Okay, good morning. Let's begin the second day of our amazing workshop. So thank you for coming this morning. I hope you had a nice evening last night. And I'm happy to see many people here for this hands-on session, how to use BHTOM. So we will begin with a series with two short talks, quite technical. So don't feel, if you don't follow everything, then it will become clearer later, because there will be some technicalities we will then try to exercise, right? So Przemek and Chris will show some of the things related to mostly to the data processing, right? While later in the hands-on session, we'll go back to the basics and then we'll cover also the data upload. Right, so I think we are on YouTube. The slides are here. Everything works. We can just start the slides. Where is it? Right, there you go, Przemek.
Thank you. So hello everybody. Nice to see you again, some of you again, some of you for the first time. So I'm Przemek Mikołajczyk. I'm the main developer of CCD4, which is a very basic software. Not that basic, but the idea is basic. That's dedicated towards processing fixed images. I will try not to bore you with the details, because they aren't really that important. And I guess, like most of you knows a lot about processing of astronomical data anyway. So here is the very simple schematic of how the BHTOM system works right now. Is the laser working? Oh yeah, okay. So the network of telescopes collects a lot of data, and it's very non-homogeneous data. So this is the basic problem that we have with these observations, because if we want to get science-ready light curves, then the best way to go forward is to process the data in a homogeneous way, ideally with one set of software. So the CCD4 itself sits within the BHTOM right now in the second version of BHTOM. It will change, it will multiply in the third version. But basically, it's one of these two processing codes. CPCS is the one that standardizes your measurements, so it moves the whole photometry towards the standard system, but CCD4 itself is the one that reduces your 2D information to ASCII magnitudes. So it doesn't discriminate between the type of image that can be reduced. So CCDs and CMOSs are equally okay. It is entirely built from blocks. So you can use one of the blocks. Maybe you want astrometry, maybe you want photometry, maybe you just want Gaia astrometry or anything else. Maybe you just want to standardize your FITS files. So these are the capabilities that are within CCD4. From the change from the first version, the main change is that the first version was simply the spatification of the code. So it was just, you were putting in the image and you were getting the results and nothing in between. Now we are providing quick look plots, so what your image looks like when it's going into the pipeline, what it looks like when it goes out of the pipeline, and we try to show progress and provide feedback for our users. But as most astronomical software, I guess, it works as a black box. So when you put not so good observations into it, you will get not so good results So it will make the best of it, but it will not. It's not able to. Yeah. So it will not do magic. And one of the capabilities that we are now, it's already implemented in the second version, is that you can install it on your standalone computer. So if you have a server in your observatory, you can just install it on your computer and use it as a processing pipeline within your network, but you don't have to do any setting up. You just have to register into the BHTOM, create your observatory there, and then apart from providing the feeds file that you want to process, you provide the name of the observatory, and we pull all the characteristics of the CCD, all the characteristics of the place, observatory, and everything else from the internet. So it kind of was designed to get a load off you. Yes?
Yeah. You mentioned astrometry. Do you require that precise coordinates are already in the header? Or can you recover astrometry afterwards?
We always perform astrometry ourselves. I guess you can choose that your astrometry is precise enough for further steps to go forward, like photometry and so on. But we don't want to trust the users, because we find out that even the best telescopes provide wrong astrometry. Yes. And that probably would be the reason why you asked that. Yeah, like VST or, well, I will not mention telescopes here, just not to, you know. All the users are fantastic. Okay, so yeah, the second version will be talked about more by Chris in a second. So just to give you a brief overview what CCVOT consists of, not to bore you very much, it uses all the Bertin, Emmanuel Bertin software like SCAMPS, Extractor, PSFX, and so on. We try to use as much Python, AstroPy, and so on as possible, but in the places where these routines, AstroPy routines, are not quick enough, we use compiled code, mostly WCS tools, ISO Eclipse, and so on. It's already there, so why to do it again? And till the end of the last year, to the beginning of this year, we used PyRAF and IRAF, which was horrible because it gives a lot of errors. It's not supported anymore, so it's in the gray right now because we managed to get rid of it from the pipeline. So, yeah, I want to meet the person who claps. Okay, so just to put a quick overview of what happens within the CCD file. The whole idea did not change. We just improved on the steps. We want image looking like this, and we want to give you image looking like this, and get rid of all the stars in the field of view. Not only of the stars that are present within Gaia survey, no matter the version of the data release, but also we want to measure the sources that are not in astrometric surveys, so like non-sidereals, SSOs, and other things, like transients, maybe new transients appearing in the field of view. So the three basic steps are, just will not talk about that because I already covered in the past in some extent. The three crucial steps. First is automatic selection of stars for PSF model. Basically, you could not do that till Gaia appeared. You could try, and you could do it very, very well for one observatory, because you know it, and you could improve on the method, improve on the steps that you have in your procedure. And it was done in the past very well, but only for you have to do the work for each observatory separate. We wanted to do this in an automatic way, so we wouldn't have to interact with the process at all. Of course, Gaia gives you great precision of positions, and it also gives you the great precision of positions of neighbors. So in the entire field of view, you can actually look for the stars, take Gaia measurements, and say, oh, this star may be contaminated, but some other star, and so on. So we want them evenly distributed throughout the field of view, so on. Then we perform all the required steps and deliver results. Results consist of astrometry, which comes in two flavors. First is just the astrometry in J2000. And the second one is the astrometry in Gaia epoch. So the DR3 is 2016, and then is the 2016 moved to the time of observation. So if you gather this astrometry for a long time from all your images, you also get another data product, which is astrometric time series. So basically you can extend Gaia into the future. And yeah, and we provide photometry, which is profile photometry, and two aperture photometries, one cone-like and one circular. But we plan to also finally introduce PSFX, profile photometry from Bertini, which I'm not sure that it provides better results, but it's always good to have more of the products just to be able to switch between them, because you can easily find out that when you have two different fields of use, in one aperture photometry will be better, of course, because it's not dense, and if you go to the bulge, you need some profile photometry for sure. Yeah, so when you use it, like in BH-TOM, we don't only measure the one source that we are interested in, but we measure all the sources. So after years of observation of, let's say, Gaia Ayers rock was 16 AYE, we have time series for all of the objects. So we did some preliminary studies in University of Wrocław when one of the bachelor students was given the data for this object only from our observatory, Białko Observatory, and he did some rough calculations without the need for very advanced analysis, and he found like 20 new variables. So I guess BH-TOM already is a mine for not only for transients, but for variables for sure. Okay, some examples of the automatic processing. So this is what it looks like. I am not interacting with it. It just selects the PSF stars automatically and subtract all the sources or all the sources I want the pipeline to subtract. So you can see here, it did not subtract everything because it selected like a skewed field of view. Okay, you can clearly see that the fringing is visible much better here because of the difference in contrast. This is the same field of view. This is in I and this is in R, probably. Yeah, and the before mentioned Gaia Ayers rock looks like this. So, yeah.
I was wondering, do you ever compare the residuals after subtraction with the flat field? You see?
Oh, yeah. This will be the final point here, but this is actually, I think it's here. So just let me take a look at it. No, it's visible, I guess. Okay, so yeah, concept didn't change. We abandoned the simple pipeline concept. So Chris will tell you more about the Dockerization. So we completely removed requirements from the users, so you can use it as a black box. You don't need to specify what is your camera. Basically, you don't need to specify anything. If there is exposure time in the headers, if there is a start of the observations in the headers, that's all we need. If you don't provide gain, if you don't provide readout noise, then your errors will not be will be farther from the truth. But you can reduce such observations. Yeah, we added new methods for performing astrometry and photometry, basically improved on them, and I think it's here, we removed outdated software. So the second CCD is only in the Docker environment for everybody to use, and we are GitHubbing it right now. So the first like alpha tester who will test in bulk will be LCO, and they need such a software. So after a short while, we should have great feedback because they produce a lot of data. And the first CCD is now installed in BHTOM still. And we are not planning to develop it anymore. We just abandoned the idea completely. So what is already achieved is in the white. What we work on is in the gray. So we would like to add the support for processing whole nights, for you not to have to create another pipeline. Just put the tar.gz or zip file or whatever archive you prefer into the pipeline, and it will just provide you with photometry. We have the support for non-side-wheel targets. We actually have it for a long time. I was asked a year ago by Nicolas Erasmus from SAAO about it, and we tried to do it via BHTOM, but it appears that BHTOM does not support it's non-side-wheels. Yeah, so that's the problem.
It was removed from the
It was removed, yeah.
and we will put it back.
Yeah. So just to
Sorry, what was removed?
The
non-side-wheel.
Right.
So you basically you weren't able to even grab the proper characteristics from the net base and so on. So yeah, the PSFX is very easy to implement. So we should be able to provide the second profile photometry, which I would not count to be worse than the DAOFOT, but I guess it will be slower. I went through a lot of astronomical software for photometry, and nothing was faster than DAOFOT. But there is a guy in Warsaw who's rewriting the DAOFOT to C, so we'll see. Okay, IRAF, yeah?
Did you look at DuFont?
I did. I do mean the old software, but this is basically the same. This is basically the same. It was within IRAF, the first IRAFs, right? You mean this one?
DuFont.
Yeah, DuFont, yeah.
But that was
That was
together with Gaia.
yes.
One of the
Yes.
I used it as a standard line.
But
Yeah.
the same like
Before the DAOFOT was introduced into the IRAF, the precursor was DuFont, and it's basically these are the same routines. The Stetson just improved on the code and made it more reliable. Maybe he provided the user with the ability to change some things on the fly. But still it's Fortran, it's not really scriptable, but we made the wrapper for DAOFOT within the CCD-FOT. So if you want to run photometry with DAOFOT, you don't have to use Fortran anymore. You don't have to install it. You just made the photometry for one Wi-Fi with DAOFOT, and it works. So it also can work as let's say if you teach students and don't want them to know about Fortran because it should just keep it quiet, let it die in let's say 20 years, 30 years, then we don't have to really show that to them. So we removed finally, after so many years, we removed IRAF, PIRAF, and I don't know, DAOFOT wrapper in Python added, yeah. So in the future, we would like to provide the quality flags. It is now kind of conceptualized, and we would like to do it in a way that you know whether the moon was close to your target, or maybe the calibration was bad, because we can tell actually that calibration was bad during the calculations, and that is it should be somewhere here. Yeah, I don't know why it's not visible. It's changed in Łukasz version, but basically, it's here that the final step that we would like to add in the future, which I was aiming for years, is that we give you some kind of feedback in terms of your calibration process. So if it was debiased, darkened, what was flat corrected in the right way, you can actually see that exploring the residuals of the image. The most common thing is the gradient across the image. So if you have the gradient across the image, and let's say that you did profile photometry, it's not that bad. But we're using aperture photometry, then it's really bad. Then we can see that we can see these gradients, we can see the calibration quality in our data. So one observatories really provide top-notch observations, and some just don't. Yeah. What else? Just to tell you, yeah, the feedback. This is within the Dockerized version, but we would also like to show it to you in the BHTOM itself. So people were complaining that you are uploading an image and you then don't know what happens to it. So we can actually tell you that it's being, the astrometry is being performed, then the photometry, maybe there is some checks, maybe there are some errors. So the feedback for the user in terms of what really happened. That's very important. We will find it also unloading a lot of work that we have to do contacting users. So hopefully soon it should appear, maybe in the BHTOM version 2 even. Yeah, for sure. Okay, so the thing that really hurt us over this, let's say, 4 years is the fact that we did not store all feeds data, at least for a year. We should have been doing this since the beginning. We didn't process that much. It would take one external drive, maybe two, to have all this data. And then now, after so many corrections, we could process it again much quicker, but in much more reliable way, using all the things that we learned from the users over these years. So I hope we will introduce such a thing like external storage. Yeah, star subtracted images for eyeballing and some kind of PDF report for each file, so showing you the quality of each product, and Chris will show you how we want to do it. We have some preliminary ways of determining which photometry actually is better, not only in terms of the whole image, but also in terms of the object of interest. And yeah, and this is the perfect reduction software for your observatory. And if you would like to use it in the future, it's going to be very easy to install, just downloading from GitHub, without the need of these tedious tasks of first installing Atlas Algebra package, then installing IRAV, then installing DARFOD, then doing all these things, because it could take, sometimes it took days to do it right. Right now, we will just rely on 3 dependencies. First one will be Python, 3 version, I guess. Or everything is now in 3 version, in 3.10 and newer. Docker, and the probably Luigi, probably Krzysztof will tell you more, but some kind of other Python package which is easily installed to manage the interaction between the Dockers. And that's all. You don't need to install anything. Take your image, process it. And then hopefully you use it for your science, and cite us, and bring us to your observatories, give us jobs, and so on. That's the conversation for later, I guess. So thank you so much.
Okay, thank you, Przemek.
Thank you. I don't need even the date of observations. If you don't give it to me, you will not have the time series. I don't. I kind of assume that if you are not providing the name of your observatory as it stands in the HTOM, then the date keyword should be date dash ops. The exposure time keyword should be exposure or x time. And if you have those two, you can reduce the image providing the timestamp and the magnitude. But the errors will not be true errors because you don't have gain, readout noise.
I agree, but my question is mostly on, you have two sets of data, like you have one set of observations in alpha filter and another one in zeta, right?
D filter.
So how does the program know which sets should be divided like flat filters?
We are not doing the calibration, it's the reduction.
So
This is a common misconception between those two processes. So reduction is taking the 2D information into 1D information or multiple D information. The calibration you have to do for yourself. And I don't mean this standard calibration. I mean the flat fielding, biasing, de-biasing,
So this should be first
Oh, yeah.
calculated and then filled.
For sure. We could do it for you, but we will never be as good as you.
Okay.
That's the approach.
This requires a specific knowledge about the instrument sometimes. So we don't get to get involved into that. Yeah, sure.
How fast does it run, and is it feasible for you to run it in real time as data comes in?
Oh yeah. Sure.
Well, it depends what's your date,
Yeah,
right?
if you
Data
have,
rate,
say-
right?
Say 5 seconds.
5 seconds.
5-second time series. Yeah. It depends on the field of view and it depends on so the bigger problem with such softwares is that Python is not really what's the proper way, multi-thread. No, we don't use Python for any calculations. So we just use Python for like what is your HJD? It is fairly quick, no difference, right? But if we do any proper calculations, we use compiled programs. If you have, let's say, a machine with 8 processors and 16 threads, then 16 files can be reduced at once.
Yeah, so the version we run is parallelized, right? So in that sense, we can catch up with your data.
We cannot employ multiple process threads to do one thing, which would be perfect for this 5-second time series coming in. But as long as the field is not overcrowded, this is also the choice between the quality and the speed. We could choose, let's say, only 2 iterations of PSF fitting, much quicker, but much worse, right?
You and the processor scales up the number of cores. So
Yeah.
you always add
That was like-
the moment the
Exactly.
system breaks down.
That was actually the idea behind the whole software is the idea of my supervisor, Mr. Kołaczkowski, who wanted to build such a thing for our observatory that you observe and you can see it was basically built around Gaia 16 AYE. So we observed it at the very peak when Gaia was observing it. We are doing it at the same time and we saw the magnification in real time. So this is perfect for eyeballing the result. Let's say in
That's the
real
goal,
time.
right? We want to have the feedback
Manuel
as soon as
was
possible.
going
Yeah.
to ask us what.
And once you have it Dockerized, then going to Amazon or Google for farming it out on the cloud, you can have thousands of.
That would be the end game here. Yeah. Just have a really huge cloud and run it really quick. Even if you have to wait, sometimes in astrometry.net you really have to wait. It can be 3 seconds, but it can be 10 minutes. So 10 minutes is enough to provide profile photometry and other photometries as well for a really dense field of view for us.
Ready for download? I have
We made an arrangement with LCO that they are going to be the alpha testers for the Dockerized version, but basically we can run it, we can show you how it works. We can also give you the copy of it, yeah.
Okay, just for the, to keep the time being used until the coffee break, so let's have another talk about the details of Crete.
Hi everyone, I will be talking to you a little bit about how the process of the Dockerization of the CD-FOT went. And to do that, first I need to tell you why we did the Dockerized version of the CD-FOT. So basically the main reason is to eliminate the problem that works on my machine. Because as Przemek already mentioned, in current state, this CD-FOT is quite heavy pipeline that requires a lot of dependencies, and the installation can take up to 2 days even, and it's not quite it's not easy, and it can even fail sometimes on some machines. So this is the main reason why we need to have this whole pipeline, all the dependencies, all the packages of the code into a Docker, into an enclosed environment, so it can run pretty much everywhere. So this gives us also some improvements, because it gives us consistent results, because the runtime is the same, and there is the same environment for that. We can also scale it pretty much easily. And what we did during the process of Dockerization, we also simplified some of the routines, some of the code, so it is much more user-friendly, I would say. There was a lot of this kind of spaghettification of the code, so now it is not. It is much more cleaner and easier to read. So if someone would want to get into the guts of this code, he would not get lost. So basically the whole architecture of the Dockers consists of several containers for different tasks. We have decided to move in that direction because we wanted to have we wanted to be able to perform different tasks at different times, and sometimes we wanted to do some of them and some of them not. So we needed to have this kind of approach. So I will just quickly go through what those Dockers, those containers are. So the first one is called Fitzman. It is just solely to handle Fitz images, Fitz headers. So to canonize them using tools such as Putzers tools and Python. We also have the option to link it with the BHTOM API to download the information about your observatory, but it's not essential. It can work without that in the Dockerized version. And we basically manage Fitz headers, so each keyword is in its canonized version and has the same format. So we also provide at the endpoint, we provide nice and consistent results for the Fitz headers. What it also does, it is an improvement here in that version, that we use star lists from also Gaia DR3, UCAC4 and TUMAS, so we can have much more complete version of our star list that goes into the further process. And what it does, that it is a new approach, that it is an approach that it is needed per object. If you upload your image and we need to download the pipeline needs to download the star list from those catalogs, but then it is stored in a cache for further calculations. So if you supply a new image, it will not need to download those things again. It will just make a cut of the star list that is already downloaded. So then moving on, we need to perform astrometry. So we have astrometry that we do ourselves, and we also use Dockerized version of Nova Astrometry, which is publicly available. The Docker is already made. So this is kind of a last chance astrometry if our astrometry fails. And we use that for that purpose. Extractor SCAMP with URAT and UCAC for catalogs, also NOMAD1 to mass. And then after astrometry, of course, there comes photometry. For photometry, we have DAOPHOT and the Astromatic software. Astromatic software will consist of Sextractor, SCAMP, and SWARP, but mainly Sextractor, which has chrome-like aperture photometry, and also we plan to include profile photometry with PSFX. Now profile photometry is done with DAOPHOT, which works great also, by the way. But in this version, DAOPHOT is wrapped in Python. We provided the wrapper for DAOPHOT in Python. It is not like a full wrapper that you can do every task that DAOPHOT can do. This is just a wrapper for those tasks that we needed in our pipeline. So it is easier to do that, but it cannot do every task that DAOPHOT can, but it is designed in that way that you can easily add to those functionalities. So we do, of course, aperture photometry, profile photometry, and then NEDA photometry, NEDA aperture photometry. So those products are then in the results of the pipeline. And here we also needed to kind of assess the quality of the photometry that we provide. And for that, we use this kind of approach that we take the magnitude errors of all the measurements in the image. Here in this not yellow but green square is the target object that is our object of interest. And in this way, when we fit, we do a GAM regression of that data, we can filter it based on the outliers. We can also calculate some statistics from that. And we can, in that way, we can compare each photometry, profile photometry, aperture photometry, NEDA aperture photometry, and also Sextractor photometry. So we can assess which is the best. So this is the plot that kind of shows you how the results of the photometry are. The magnitude error, of course, increases with magnitude. The lower the magnitude, the higher the error. And based on where our target object is, we can combine it with the statistics, and we can place it on that plot, and we can see how good the photometry is. And after all that, there is another Docker, the last one, which provides the results. First of all, there is a full log from the pipeline. You can see each step in detail, what was processed, how it was processed, and also the results of each step. There will be a summary in PDF, in the form of PDF, the summary of the whole process. Also, we provide PNGs and FITS files with both original and subtracted images. And as I've mentioned, the automatic quality assessment of each photometric product will be also in the results. Yeah. So to make it all work together, so the Docker version of the CDFOT is easily installable and easily run, we needed to find some kind of workflow management system to handle all those operations. And this is the solution that we came up with and we want to implement, which is called the Luigi. It is a Python package to manage the processes of basically, it can do manage processes of a lot of we say pipelines. It has application in the scientific pipelines to make the process of processing the data easier. It is an active package that is constantly being developed and updated, and it can monitor each task. It can handle dependencies of each task, when it's run and how it's run, and if it can be run if some tasks have failed or if have succeeded. It can manage all of that. We are also monitoring each task, the result of each task in a JSON file that can be easily read and also can be combined with the future API for the CDFOT. In that way you can process and you can see the progress of each step of the pipeline. Yeah, okay, so that's basically the idea of how we would like to manage the whole system. And I would like to present you some examples of the results of the images that were processed through the pipeline, through the Dockerized version of the CDFOT. And these are the images that the current version did not handle well. It gave errors, and there were problems with processing this data. And we were actually surprised when we ran all of the errors through our Dockerized version of CDFOT, and all the errors, errors that we get from the current version of CDFOT just went through the pipeline and were quite well processed. As you can see, all of these stars, on the left there is an original image, on the right there is the image with stars that are subtracted, and you can see this is quite a sparse field of view, so it did quite a well job in some denser field of views. Also, we can measure all of the stars, and even when there is like kind of a problematic image, we can see a lot of vignetting here. But even if there is like a problematic image with not so many stars visible here, this version of CDFOT processes really well and provides the good results. Yeah. So this is it. This is the correct version of CDFOT.
Any questions to this part? Have you considered the other package for manage the pipelines like Prefect or something like that?
We did not actually. I don't know about that one. We can maybe.
So I really recommend the
Yeah.
Prefect from Python
Okay.
framework for the data pipelines.
I did some research in that area, and I did not stumble upon that. Actually, there were also some others like SnakeMate or something like that, but we also considered like a Docker in Docker version.
Yeah.
So, yeah, but it might provide some computational issues, performance issues.
Right. I don't see any more questions. Thank you, Chris. Thank you. So now we have time to play with. It's a playtime for BStorm. And the way we'll do it, I have prepared loads of slides, and I'm happy to share. You will get access to all of these. So there will be some guidelines in that kind of visual manual. But we will try to do things. I don't think we will do things in parallel because everyone has different speeds and so on. But we will try to do some tasks, selected tasks with BHDOM, hopefully giving you a feel what is there and how to use it. And I realize that people are at different stages of how comfortable they are. Then just let me have this here. So I call it a visual manual. So the first thing we'll start with, and I've seen some people started doing it already, is the registration, okay? This sounds simple, but it has its challenges. Yeah, I didn't put the link here, but you have to memorize the link. You go to bhdom.space, and I hope everyone has their own computers now and access to the internet. So who already has an account created? Well, most of you. Okay. Space. Right. So people who already have their accounts, you can log in and then go to your, I put it here. Go to your account, log in there, go to your username, go to your profile and double check if you have correctly put the LaTeX name, your affiliation, the address, and then about me, whatever, and ORC if you have one. Okay, good. Sure. Because why we need this, I want to emphasize this. I don't know about you here, but many people just skip this, even though these are required fields, they skip this part. And then when we write a paper using the BHDOM data, as I said, we track each observer and each person who contributed to that particular object. And then we could, in principle, generate the outer list automatically. But if you haven't provided us with these details, we have to spend precious time of us and yourself as well for this communication, which we can very easily avoid if you just do it once, if you fill your details here.
Lukas, sorry, just the beginning. What is the web address exactly?
bhdom.space.
Because I have still an old one, bh/com/astronauts.
The main one to go to is This is the link. It's a link which gets you to the most recent version of BHDOM. That's why this one should be remembered. And gives more flexibility.
And to be registered, to create an account, you must click on the top right button, right? It's here.
Yeah.
Top right button.
Register. So yeah, so this is an example paper, right, where we have all the authors. In principle, we can generate it automatically, right, if people have provided the details. One thing which we miss, and I'm sure there will be a question about this soon, one thing we miss is multiple affiliations, right? So our user model doesn't include that. That's a point to Lindy to remember about this, so that there could be a button saying add additional affiliation, right? Which we don't have at the moment. And then again, well, the ORCID number is also very useful because more and more journals use that. It's optional, of course, but if you have one, if you don't have one, you can create one, but it actually identifies an author or researcher uniquely. So these are, very basic things, but they're very, very useful for us and for yourself as well. Okay.
keep the LaTeX label.
Why?
Because you can use a package that allows you to put your real name and it will be LaTeX later.
We can add this, yeah, of course. But well, some people want to have their particular way they want to be displayed, right?
That's why you can paste it. You can write Polish letters in LaTeX and still make them look well.
Sure, sure. For example, I tend to use this version, right? Some people tend to have full name and then just a letter of their second name, right? So it's all up to you to decide how do you want to appear on papers. What's your common practice? Okay, I see people are working on things, so I'll let you. Yes, please. So the main thing, if you're creating an account, then it goes to us, right? And then we have to verify it. So there is human vetting on users. I think it's useful because from time to time we get robots registering, right? Well, not that many so far. Now they're listening us on YouTube, so they will go to that web page. Hello, robots. But the thing, it goes to us. Many of us are admins in that system. So we get an email. So, if you do it in the middle of the night, then don't expect your account will be approved immediately. But very often there is someone on duty who will click and approve it. But what these people do, these people look through your registration, and the main thing we check is about me, right? So essentially, this is crucial to say, why do you need that system? If we know you from this workshop, for example, we can say, I've been to Crete workshop, I like to try test BSOM. It's perfectly fine for us, and then we approve the account. But if you say nothing, right, or if you're a student, it's good to mention a little bit, few more words, who you work with, why do you want to use it. It gives us some, human interaction with potential users, and we know why. We don't keep any statistics of this. In principle, we could, but yeah. So many more ideas for this user model is that we can have a menu, a scroll down menu that says I'm a researcher, I'm a student, I'm a journalist, I'm a hacker, whatever, right? We can think about these things. So this field is required, and we read this, and then we approve your account. And then you get an email that your account has been approved, which means you can log in. So the thing is that you cannot see anything in the system unless you're registered and approved, right? Not even the target list. You cannot download any data. You cannot see which targets we're observing. That's the way we decided to go. It is all easy to access. It's free to access. However, we only allow registered users to see what we are doing. I think it's fair towards everyone, all the users, that we keep our community kind of shielded.
So if we're registering now, we're going to be approved now.
Yes, Pavel is clicking approve.
And it's worth mentioning that we don't have the form. I guess we don't have the form to recover password.
We do.
But you can do it for a user.
No, there is a forgot password. Can
you show that? It's a new feature.
It's a new feature. Yeah, see. Yeah, you see, if you go to login, forgot password.
Because it wasn't here in the past. Okay.
It's been here for a while, so.
It had to happen to it. The PHP2 is so powerful.
Well, the only thing you can see if you're not registered, then is you can see the about, which I really apologize, it's still work in progress. There's not much there. But we try to, it's just a very brief description. You can have the list of recent changes here. There is a link to the newsletter I mentioned yesterday. so it goes directly to the mailing list there, and there is a link here to draft version of the documentation, right? So if you ever need to, you can do that before registering, and then if you go to the documentation, it brings you to our public GitHub, which is, this documentation is still very, very limited. We'll try to work on it. Apologies. However, this is the easiest way to get to the API documentation, which is very extensive and complete, right? So again, you go to About page, there is a link to draft version of the documentation, and then you can go to the link of for the API. And actually, you see here some recordings from last year's workshop directly here. So instead of the documentation, we have the recordings. So the things we are showing now, right now, they will also go here. So you'll be able to listen to me again and follow the same instructions. Oh no.
Is there a list of registered sales sites?
You can see that after you've registered, of course. Yeah. I have a slightly different view. Don't worry about this. You will have less things on the menu here because I'm an admin, so I can see some things which are still in the development. But if you go to the observatory and then to the observatories, this is where you get the entire list of all telescopes we have. And how many we have? 109, 109. Yes, Moritz.
Will there be a way in the future to link the observatories to the actual data points in photography, for example? So for an event, we can look at a data point to actually go to the page where the observatory is listed.
I don't think I could hear you.
So for
Say it
example, for the photometry, if I need parallax, in the light curve or pit parallax, I need the coordinates of the observatory. And mixing and matching so that which data was actually from which.
Right.
It's kind of difficult.
But it already exists.
Well, kind of.
You can browse through the data point from.
You can.
Yeah.
So,
But
I don't see anything.
one click.
We can get the name of the
all the
telescope.
characteristics like location, altitude, and all the other ones are in the system.
Okay, we'll get there. We'll get there. So maybe it will. It is a valid point, but it's kind of already there. Right. So I hope people went through the registration already. Is anyone still working on the registration? Well, you are still. Okay. But let's move slowly to do other things so that I'm thinking how to do it in parallel so that people can. Okay, we'll get there. I have an idea. So the main thing actually you get after the registration, kind of the main landing page, is the target list. So the target list has maybe I'll show actually the actual place. If we go to home, right? The home just gives you this nice image and some latest comments. You can see what was commented recently. There are also links to the documentation. But the main thing we start with are the targets. So go to the target list. So this is kind of our main starting point. So you have an interactive map, which you can then look at, and then you can click. I'll get there later. So this is the list of targets, which are, so these are the targets sorted by observing priority, right? So at the very top is the target which has the highest priority for observations. And the priority is computed with using the values of importance, how important the target is. We'll create a target, so we'll see what it is, and how frequent we will want this to be observed. But let's do a thing. So here, that on the target list, let's go to filtering. Let's play with this. And here we can work actually independently, all of us. You can search for targets through different fields. So you can type in a name, right? You can select classification. So if you're interested in RLIRI only, then you can just select RLIRI. You can type the description, some words which are then used if the word you typed in is included in the description, then you can find it. Then there is a con-search where you specify array, DEC, and the search radius, which probably is going to be the most useful. Target grouping, we have groups of targets. You can create your own groups if you like. These are publicly visible, but you can actually narrow down your filter to the group we have. Yeah, target grouping is there. We'll get there in a second. You can search around the target, which is also handy. Then you can type in the actual array and DEC searches. So that's like a box search. You can also search using galactic, longitude, latitude. And then here we go to the importance. By default, the very first page you open, it already marks the minimum importance of 1. So our convention, this is very, very convention of our system, is the importance goes from 0 to 10, and we assume if the target has 0 importance, it doesn't mean it's not important, but it means there is no need for any follow-up, right? That's our convention. So you can enter a target which you like to investigate just to see what kind of data is there, but you don't need any further follow-up. Then while creating this target, you give it importance 0. So then all the telescopes, they know this is target not for observations, right? And everything above 0 is then considered as a target for potential follow-up. And here it goes from 1 to 10, right? If it's 1, maybe an occasional data point would be useful. And it actually, the value of priority is then computed using this importance. So if the importance is 0, then the priority is 0. So that's our convention.
And that's entirely determined by the user?
Yes. Yeah. It's very subjective, and we then kind of verify it. If you type in 10 and we see that your target is like a slowly varying variable, then we would lower it down, right?
But we can update that.
You can update it later. You can, well, as the event evolves, you might want to. For my cleansing events, it's the very common case. When we discover it early on, then we typically say, okay, we need this target to be observed every single day. But then, if it goes to caustic crossing, we boost it up so that we require way more dense and way more higher important. And then after the event is gone, we lower it down to 1 because we need some data points after the event. But then it's less crucial. So this is very subjective. You need to practice. Yes, Michelle.
I have a question about, say, the observatory. In the observatory, the beam detector presenter that I have seen, and it says billing 111, 1 times 1. Sometimes you use it in billing 2 times 2.
Yeah.
Do you have to enter it as a new observatory?
No. So there should be a comment there, but we'll get back to that. We will get to it.
Yeah, we'll get to the point.
There should be a comment that this is the lowest billing that you are using. If you are using 1 by 1, 2 by 2, 2 by 3, 4 by 4, you always put 1 by 1. Just for the general knowledge of the worst pixel scale that you can offer. Because when you doing certain campaigns, observations between the different observatories, then the pixel scale really matters, right? So you, by putting 3 by 3, give us information that
where do you enter that?
It should be in the creation of the observatory.
We'll get there in a second. Okay. Simon, yes.
What do the ticks imply? Ticks on the right.
What are the ticks? I don't know. Lindy, do you have an idea?
Just looks cool.
Maybe.
So you have to enter stuff in all of those fields.
No, I think it actually shows what kind of field is
It's just a
this.
valid field, so if you type
Yeah.
like a couple letters into the current search.
Okay, so for a target name, you could just put the first few characters and then
And you will get the list of the targets with that pattern.
You can play with. If you just say Gaia,
yeah.
it will give you all targets with the name Gaia, right? Even ZTF.
But how did you get that? For sure. Did you click on the
Well, the thing is that it goes through also through other names, right? Each target can have multiple names, right? If there is any Gaia name as one of the other names, those will also find it. Well, just click here, filter at the bottom. That's the job. But I just want to stop talking about this importance. If you want to get all targets, you just can empty this field or type in 0, right? And I will remove Gaia. So now it's essentially an empty filter. Then I'll get all targets. These are the all targets we have in the system.
Oh, wow.
And it's very slow. Simon.
I have a question. Maybe you're going to come on to this, or maybe this is not a feature, or maybe I'm being stupid. But is there a relationship in filtering to the observatory and the target? I.e., can I have a list of all targets observed or parts of observatory? The observatories that would see this?
It's not built into the GUI, the interface here, but I have scripts for that because all these things can be scripted from your own code, and that's easily done from a notebook, right? We do that. We can do that with VStorm, but not on the web page. We'll think about it. It could be useful to have it on the web page, but I think it's way more useful to have it available through API. That's right. There's an API. Yeah. With API, you can query the targets, and you can filter them on the visibility or whatever criteria you want to apply, right?
So, that's typically, LCO will show visibility for all the sites, but that slows down the way.
Yeah, exactly. We want to keep VStorm fairly simple, and then let you do all more sophisticated stuff through API, right? We actually want to encourage people to do that, instead of us adding more features on the web page, right? Right. So I suggest now people go play with the filtering, find your favorite target, maybe we have it, right? Or see what kind of targets we have, find or see all the microlensing events, or filter on the galactic, whatever things you have. I haven't talked about sun separation. So this is very generically telling you that this target is going behind the sun. That's it, right? So it's a proxy to the visibility, because this is uniform for all observatories. And then the last magnitude is also what's the last magnitude, right? And we try to homogenize this last magnitude. So this is whichever magnitude is the last, we try to calibrate it to the more or less Gaia magnitude, so that then you can compare the targets, right? But that's a detail. Okay, you can play with that. There is another list, which is called visual list. And it's the same, filtering. So instead of doing the other targeting filtering, you can do it here as well. The difference is, if I go to microlensing events, and then I say, okay, give me all microlensing events above 1. The only difference is that instead of a list of targets, it shows you light curves of targets. So that's my personal favorite. You can just quickly scroll through all the light curves. Whereas if you do the regular filtering on the target list, you get just the list of targets like this, which you can then click, and that brings you to a target page.
The filter, what is the, what are the units for the right ascension and declination?
Degrees.
Degrees.
Yes.
And it's decimal.
Decimal degrees. Yeah.
Which is not very, it should be switchable.
Well, it's computer friendly, not human friendly.
There is no information, there is no placeholder for the units.
There is no information in most of these things, yeah, but this is what we are working with.
Ah, yes, we should add it that it's in degrees.
Exactly. All these points are very.
So you see, here you have essentially an interactive page with all light curves, so you can very quickly see if there is anything what interests you, and then again you can click on this, and that brings you to the target page. Let's see here, for example. So see, I can go to a target page from whichever, either from the target list or from the visual list. So I hope you managed to find some targets of interest.
If you go with Gaia, there is all the non-Gaia targets have Gaia source ID. So you for sure not do that.
No, I think this can do it. This is possible to do it if you get information from ZTF. Sorry, from TNS.
I don't know as well. But this is also a good fight for you. How to display all the. Lukasz, what is the answer for Simon's question? Because we want to know it as well.
Is that in Gaia?
No. Yeah, but all the targets have Gaia source ID, so we will show all the targets.
Well, it also depends.
Right? There is Gaia word here.
No, look, this target has Gaia alert as name.
No, but the question is there are two meanings. If Gaia discovered it, so if Gaia was first, or if Gaia alerted it. So
No, if it has Gaia name.
Ah, then fine.
Yeah, that's it, right?
Can you show that?
So I just did that.
Just to filter Gaia.
Okay, I want to show.
Well, we can do it here, right? In the visual list. Where did it go? So let's say we go for Gaia here, and then we remove this. Right, you see Gaia? You see that? And importance 1. So all Gaia alerts which are now of interest.
Can you also set importance here?
Yeah, you can.
So I can't. So show me how you do it. I cannot edit that.
You should be.
Maybe it's Safari.
That's weird.
I've also done it.
After a while, you can take out of her. Use it then for other things. Łukasz, podnieś to, że jeśli mam jakieś problemy, żeby od razu mówili.
Tak.
Jeśli ja siedzę, wiesz, robię swoje.
So there are people who are here ready to help you, right? So if you have any issues, then shout, give us a shout. We can help you directly with your problem, right? So I'll be talking here. I hope I will be not interrupting too much. You can follow me, or then you can
Also,
do your
if you
own
need more time
things.
to
Yeah.
just let us know.
So we can find all Gaia 20 4 targets, right? For example, Gaia 24, and then we don't say anything else. And that will bring us, to a list of, yes, David.
Lucas, may I ask a question? Lucas.
Oh, yeah, okay.
Yes, yes.
May I ask a question? I mean, the target list which Lucas just uploaded or asked. I mean, does it show the importance as first and the most important as first and the last important as last?
Just a moment, because Łukasz was
Sorry.
busy. Yeah.
Hi,
Yes,
Lucas.
Josh.
The target list you just showed, does it show the importance as well? I mean, the first one is the most important and the last one is the least important?
Yeah, on the target list, actually what we display is not the importance. You can sort by the importance if you want. Just a second.
Not in the visual list.
Not in the visual list, no.
The question was about the automatic.
No, the visual list, actually.
The visual list, what is the sorting there? I think you can decide on this, ordering here by importance.
Okay. Okay, because I never tried this visual list. I didn't know about it.
I think by default it's just a random order. Unless you change the ordering to importance, then you'll get it by importance.
Okay.
Okay, next thing we can do, so target filtering is something that we have done, but we can then add a target. So if your target of interest is not on the list, which might have happened, then we will get to adding a target to the system. So there are a couple of ways of doing it. It's also the targets menu. So there is target create, there is target import, and target catalog search, right? So target create is just a blank form. I will not go there because you will see why. You can fill all the details about your new target you want to enter. Import, you can import a file with a list of targets you want to include. But catalog search is the most useful feature. And let's go there. So you can actually search through Gaia alerts, or you can search through Antares targets, through Ogle EWS, through TNS, NET, or Sinbad. So you just need to know the name, and it will fill everything for you, right? So you can type in Gaia alerts target, Gaia 19AXP. Say, we do search. There you go. We have everything scrapped essentially from Gaia Alerts webpage. So the right extension, declination, epoch, it's classified by Gaia as quasar. There is the description, discovery date, and by default it puts the importance very high. And then you decide on the cadence you want this target to be observed. So by default, it assumes you want this target to be observed with high priority every single day. Then at the end, you can add aliases if you know their name, but don't worry about this, this will be filled automatically. And then you do submit, and I got an error because this target already exists, right? You are free to add things now which do not exist. So now is the time you create your own target. Unless they exist, then you'll get an error. which means it saves you some work because the target is already there, right? So you can go through Gaia filtering, you can go through Antares, you can go through Ogle AVS, you can go to NET, Simbat, whichever platform we provide, it will fill all these details for you. You just need to verify it if it's correct and then click submit. Yeah, I know. It's so targets, catalog search. This is where you go, and that brings you to this form. There's TNS. Yeah. You can type in. There you go. Just reads everything from TNS.
This is for search catalog for creating wait 5 hours, fly above them, then I will take.
So we have two things to write down, which are very important. One is to fly. When you go to target, you have cadence request. You should also have kingdom request. The other thing that we check my phone, Sebastian showed me something, which also is ridiculous.
There's also a clear what combination because when you
One thing to note, when you create the target, it will appear empty, right? So don't worry about this. Just wait a couple of more minutes and then hit refresh. It will, in the meantime, it's just behind the scenes, and it's downloading all the data. Apart from Atlas, all sorts of data are being downloaded within minutes. Atlas takes longer, and it will appear on, well, we only do it bulk downloads every 12 hours or so. So if your target has any Atlas data, you will have to get back to your target within 12 hours or so. No, you will only find out, because then we run the query, and most cases there is. So. Yeah. Well, no, don't worry. We can edit it. Yes. So one nice hint you can use is that there is a direct access to your target. So this is the full direct URL you can use with your name, because every target has an ID, but also it has a name, right? So this is how you can access your target, and you can share with your collaborators, for example. Just give it a direct link. Right. Yeah, I will not go through this. I will give you the manual anyway.
Not only Gaia alerts, but also
Okay, so if you can do this, the issue is this. It's very tricky to space. So doesn't make sense.
Okay, time is running out slowly. So one thing I wanted to show is that once you have your light curve plotted, yeah, that's how it looks. So here, by default, the first plot is shown by filters, and it's an interactive plot. You can click and remove things, you can zoom in and so on. Whereas there is a lower, at the bottom, there is another plot which shows the same figure, but sorted by a facility, right? So if you want to check who contributed which data, then you can very quickly plot this again. And then moreover, if you click on a data point here, you find out when was it observed, the MJD, the magnitude, which filter it was calibrated to, and then who did that observation. And this is also a link to, oh, I don't have it here. It actually brings you to what Moritz was asking. We can try it here, right? So see, this is some light curve. Right, you see, this point was collected by this observer, and we now know which observatory was collecting this data point, what's the name of it, and this is also interactive, that you click, and then you see all the details. You can actually see the actual image, right? So you can verify whether the image was faulty or not. Very quickly you can have a look and see which filter it was observed in. And then in the calibration, you see what was the calibrated filter identified. This was standardized to Gaia synthetic photometry I-band. This is quite technical, but if you do observations, this is useful. Then you can trace each data point you submitted. And this is Maurice. This is where you have the name of the observatory, right? And then you just go to the observatories, and you just look for the observatory, right? And you have the coordinates. This is the only way for now. Okay, we didn't get to any data upload. I'll just quickly show you. So let's imagine you have Gaia 19C UU, and you have observed. So you can then, in the target page, you can go to Manage Data, and this is the place where you can upload a data product, right? So here you can, what you mostly are interested in is to upload your feeds file. So you choose the files, you mark this is the feeds file. Dry run is just a test you want to do. The observer, you select which observatory was this data point collected with, which camera was used, and then this is the default that we want to detect your filter. You can write a comment and then you just hit upload, and it will feed your feeds file from your hard drive through CCD FOD calibration, and in the end you will end up with a data point on your light curve. There are some examples here you see of points uploaded here. So the only thing to remember is that now you do the upload through the target page, right? So you have your data for your target, you can upload it here. You can also upload photometry in CSV file if you have your own light curve from other observatory which is not in the system, and you've done your own photometry, like Bright, for example, right, or tests. You can upload it here, it will appear on our light curve. It will not get standardized, but it will appear on the light curve. And yeah.
Klikając w punkt można wejść w target? W ten data point?
No.
Jak się kliknie, to się wyłącza albo włącza. No tak,
Nie.
na u Maurica tak się
Nie.
nie ma opcji, że
No
podać
nie.
jeszcze raz to.
Nie.
Tak się wychodzi.
Tu klikaj.
Tak. Ale czym normalnie tu mieszka?
No.
No to...
No, if you click here.
We clicked there. And it was...
For ZTF, yes. So there is no link to data product for ZTF. Right, so, but One comment about the data upload. We have GUI for this, but we strongly discourage you doing this through GUI, right? You can only upload up to five files at once. This is just to test how the things work. If you are a new observer, then you do it once or twice, you see how, you get the feel how it works, and then you move to scripted upload, right? Right. Maybe very quickly, if people are interested, I wanted to show some scripts and then API way of doing things. Where do I have it? So there is, yeah, you can do models. I'll give you all that so you can see what's there. I don't know. Where is my, it's here. So I created a drive, Google Drive. If you rewrite the one at the bottom, it will lead you to this complex one here. So bit.ly bhtom Crete 2024. If you go there, it will be a Google Drive folder with 3 files. I'll leave this open just a second so that you can, just a moment. This is the link. Not ZTF. We'll check later. So here are some, I give some examples of these are just Colab notebooks, right? You can, of course, turn them into your own scripts. So let's have a look at the target list. You have all, I've given you edit rights. So my suggestion is you do the copy of this file, rename it to your name, and then work on your own file, okay? So that everyone can work on the same directory, but we don't destroy our own codes. Very good. This is the address here at the bottom. So this script allows you for filtering the targets, but just from your notebook. The main thing to be able to run this script, it's actually fairly simple. You need to have an API token, right? It's the classical way all the interfaces do it this way. So I did not put mine here because it's a public repo, right? But you have to get one in here. So what you have to do, you have to go to the command line, write this command, and use your username and password you have for bhtom, and it will return your API authentication token, which you can then use in all the notebooks. This is the bottleneck. We think of adding this token accessible through bhtom, which would be much easier for everyone. So you go to how to reach this page. You go to the bhtom, you go to About, you go to the documentation here, you go to API documentation, and the very first code you see, just copy paste into your terminal. Okay? If you struggle with the authentication token, let me know, I can give it to you. Nie słyszę cię. Nie słyszę cię, Milena. Poczekaj.
Teraz ja zrobię ten klient obserwator, co
Wiesz co, ludzie zaczęli robić teraz ten, ale może,
nie,
może indywidualnie.
Nie ma co się
indywidualnie
ale
dobycie.
to może właśnie pokazałbym. Bo to...
Może zapytaj, kto by chciał nad tym pracować. Bo niektórzy pracują nad API, to będziesz im gadał?
A żeby założyć, żeby nikt lepiej API nie zrozumiał, tego tyka na nich każdy stanie. Bo ten kolab jest fajny, to jest dobry pomysł.
Tak, tylko powinniśmy mieć to.
Powinniśmy to zostawić, mieć dokumentację gotowe, nawet na stronie.
Nie, powinniśmy mieć kolaba. No, już wiemy, jak to zrobić.
You are smiling like automatic.
I love it. I have a school.
Something now you can debug.
I just enjoy it.
Tu na pieprzyku, a druga jest tutaj. O, tu mi pani potrafi od razu.
So, yeah. So this is a simple, this is a good example of an API you can then change, and it will give you the target, all the targets, and then you can filter them at the Python level, on data frame level, right? And then I also filter on the last day. Never mind. There is also an API for photometry download. There is an API for statistics of a telescope. And this is an example I gave to Pirate telescope. There's my token there. So you query all the data, and then you can check who contributed what, right? So these are students of Pirate Observatory. So they are actually doing their class using Pirate telescope. So with this script, you can see who contributed which observations. We just filtered all the data uploaded for that telescope. And then we can go through all the users. So because we are running out of time now, so you have access to these scripts. Feel free to use them, and then feel free to bother us in case of any problems.
Oh, maybe there's one. Yeah.
Później będą bardziej gotowi podejść za prezentacją.
Mogą zawsze sobie wrócić do nagrania.
Tak, ja tam sobie zawsze zrobię dwa razy. Tak ci powiem. Życie wygląda inaczej, nie? No. Ale to nie jest mało. Ostatnich, nie wiem, powiedzmy 3 dni jest może z 15. Może mniej nawet. Nie wiem do czego zniknęło, do czego zniknęło normalnie funkcjonalność. Tak, ale to jest w ogóle
Move. Okay, I think we need to wrap up. Yes, I'm coming to you. I'm sure there will be plenty of questions, but I'm glad we managed to kick-start it, right? And now everyone can go into their own directions. We haven't covered how to add your telescope. If you're interested in that, feel free to ask people here and myself. We can guide you through that. We can add your telescope while here, today and tomorrow, right? In the individual conversations. If you want to follow, the path for API and have some problems with that, get back to us. So I think we should be stopping here. Coffee is already there. But feel free to talk with us and ask questions. I will put my slides with the visual manual, which covers most of these things, online somewhere, so that you'll be able to access it. Okay? Okay, we'll break for coffee, and I'm coming to you. And now I need your slides. Right, so we're ready to commence with Fabian Schussler, who will tell us about Astrocolibri.
Thanks. All right, thanks a lot. Thanks for having me. As you see, I got inspired by the nice conference poster and tried to do something similar, but this is all me and my AI friends could come up with. So I'll try to give you a quick introduction to Astrocolibri, our way of thinking about the time domain and multi-messenger and transient astrophysics and where we think we fit into this whole pipeline, and also focus on the links with Black Hole Tom. We have been discussing yesterday funding, long-term funding, things like that. That's also an issue for us. So we are currently, so we started within one of these European projects meant for the high energy community called AHEAD. This is coming to an end 1st of December. We then have a fund from the French national agency, and we are part of this new ACME Horizon Europe project. So for the next couple of years, everything is set, but then of course we have the same issues as Black Hole Tom. All right, let's start with the flow chart that you all know. We have all kinds of messengers, all kinds of different phenomena being detected by a suite of instruments monitoring the sky in all wavelengths in space and on ground. And they distribute the alert information or the detection information through a variety of brokers and systems. And historically, you all know that these have diverged more than consolidated. So you get the high energy information now mainly through the NASA GCN system. You get the optical, most of the optical through TNS, focusing on supernovae. And then you have a variety of other systems that try, for example, to do multi-messenger combinations like ARMON, and then you have a whole list of brokers being put in place to deal with CTF data now and LSST data next year. So it was due to this variety of systems and variety of data formats and brokers and streams, it was more and more complicated to keep an eye on what's actually going on in the sky at any given time. So we built Astrocolibri to pull in all that information in a single platform, in a single database. You have all the information at one point, and you can do combinations, see if this supernova is linked to the GRB reported a few days earlier, things like that. Of course, we don't want to reinvent the wheel, so we also try to use this information that we have in this platform to link back out to existing tools and platforms, so you don't have to copy coordinates from one tool to the other. You get direct access to all the detailed information that is already put in place by so many people, and a few of you are in the room. And then, of course, you want to trigger follow-up observations more and more. This is done automatically, so large infrastructures listening to these alerts, having put in place predefined TO criteria, and this is certainly being more and more important, also in the wake of LSST. But still, I think the human in the loop is important, and even if it's out of curiosity to see what's actually going on and why your telescope was triggered, but also the largest programs and the largest telescopes will always, at least in the foreseeable future, be manually triggered and run by human in the loop TRO programs. But then, of course, you have all this information, and then you can, of course, trigger other follow-up observations and campaigns. I show you how to do that with Black Hole Tom. We also have strong links with the amateur astronomy community. One example here is from the French community called RAPAS, actually very much linked to Gaia alerts, because they produced a set of filters that reproduce the Gaia color response. and are being triggered via Astro-Colibri for all kinds of transients. And then you can even go to smaller telescopes like this unistellar citizen science network, where you have then tiny telescopes, but tens of thousands of them. So this is our way of looking at it, and if I take back this slide from Łukasz, we fit in right here, right? So you have seen this whole flow chart. You get the alerts, you get these brokers, and then somehow by magic, people decide that there's an interesting supernova or an interesting event, and we think we can fit in here between these brokers and the humans, show that information in a reasonable way to the humans, who then take the decision, okay, this is an interesting event for me, I want to start an observing request towards Black Hole Tom or any of the other TOMs or networks, and I'll show you how we actually do that. So these are our interfaces. So putting the human in the loop, you need a graphical interface. We can draw on modern technology, so we don't have to read emails anymore. We can put notifications on a smartphone app, so we can do that on the go. You find us at astro-colibri.com. You see the web interface. That's what I'm going to show you, because it's nicer to show you on the big screen. But you have exactly the same functionality on an Android or an iPhone device. Plus, you can subscribe to a large number of notifications, so you get alerted when there's a new supernova being classified, if there's a new GRB detected or a new gravitation wave or whatever you want. And all of that is run in the background by an API. There's a bunch of open and freely accessible endpoints that can give it the exact same functionality. You can query our database, you can do cone searches and all kinds of things. There's also documentation, of course, on that astro-colibri.science website. I don't have time to go through all the features in the platform. I just invite you to download it, to play with it, and provide feedback to us if you see something missing or you don't understand something. I just focus, as I mentioned, on one of the use cases. So you get an incoming stream of alerts, and you want to trigger a black hole Tom follow-up. So the first thing, is that all? There is no. Okay, so if you go to the main website, again, astro-colibri.com, you see that, you see a sky map showing you the latest transients over the last 2 weeks. You get the details of these in a time-ordered list, and you can see the time chart over there. You can, of course, also change this time range if you are interested in longer time periods. The thing is, these are, you can filter them, so you have 2 rows of buttons up there where you can select, I'm not interested in GRBs or gravitational waves. You just deselect them and keep only the events you're interested in. One a bit hidden feature is if you long press on any of these buttons, there are sub-menus that are opening where you can have a more fine-grained filtering switch to your needs. So for example, if you see that, by default, this magnitude cut for all the unclassified optical transient is at 18. So if you put that to 22, of course, your sky map blows up and becomes unusable. But of course, you can then further down select that. For example, up there we have an observatory filter. So if you long press there, you have a few predefined observatories that you, if you are interested in these. So if you're only interested in the Gaia alerts, of course, you can see that from this whole bunch of observations, only these are remaining available, which corresponds to the Gaia pointings of the last 2 weeks. And of course, you can also add your custom names. So if you have a favorite detecting observatory that you want to follow, you can just add these. Further filters are more general over there. So for example, you can define, so you can pre-select an observatory for follow-up observations. So if you have TO time at any of the major telescopes. They are predefined. You can also add your own telescope. If you're an amateur astronomer, you can put your local coordinates. And then you can define the visibility. And for example, so if you switch this on, and I guess I have a telescope in the southern hemisphere, so all the northern sources are gone and you don't have to deal with them because they wouldn't be accessible anyway. And then, for example, if you're only interested in events that have been submitted from Astro-Colibri to Black Hole Tom, you can just remove all the others and only keep the Black Hole Tom events, for example. Then, of course, you have found an interesting event. You want to learn more about that. Again, you have at the bottom row there a long list, which you can also scroll left and right, of all these external platforms. One of them is the detailed page for each of the Gaia alerts that we have heard about yesterday. So if you have selected now a Gaia alerts event, you can jump directly to the relevant page, learn more about that, and of course you have all the usual suspects, Simbad, Aladdin, ESA Sky, and all these tools that I guess you know. And for example, also the amateur astronomer light curves compiled by the AAVSO, if you want to see what the source has been doing in amateur astronomer observations. So now you found an interesting event. You learned all about that through these external platforms. You want to submit that to a Black Hole Tom campaign. You can. By the way, we also build light curves now. So for all of the standard optical transients, we build light curves using data from CTF, Atlas, and Assassin. Soon also from the amateur astronomer networks, example RAPAS. We do that twice a day, but you also have buttons where you can define the start and stop time of your light curves, and you can just push a button and create one for you. So then you want to finally submit your event, so you have to register a user account on Astro-Colibri. That's quite easy, just there's this user account button up there. Then you create an account, you only need an email address, you confirm that, and then you can log in. Once you're logged in, you can go again to your user account details up there, and you have this request observatory access button, which then allows you to ask access to confidential private information or functionality that is limited to people who have access to certain observatories or collaborations. So if you push that, you get a small list. So we use that, for example, in the HESS, high energy gamma ray astronomy instruments. The SWAM mission has been mentioned yesterday, and one of the platforms is also Black Hole Tom. You click there, you enter your Black Hole Tom credentials, click login, and you're all set. So behind the scenes, and I think you have learned that this morning, we request an API token and store that connected to your Astro-Colibri account. So then next time you open the app or the website, Astro-Colibri, our interface, knows that you are a Black Hole Tom user, and you can submit targets to Black Hole Tom. So once you have done that, so you entered your Black Hole Tom credentials once, a new button is appearing down there next to these links. If you click there, you get oh no, I should have highlighted the other one. You can click on Black Hole Tom, and this submits the selected target that you have currently selected to the Black Hole Tom target list. It will then also open the page automatically of that new target, so you see immediately the archival light curves that's being compiled. You can add more information, comments, things like why you submitted that target, and things like that. And you can do that again from the website or from your phone. So you have again all the functionality on your phone. If you see something urgent or you don't have access to your computer, just do it on your phone, submit an event. One last word on other communities. So we try to discuss with our users and the users among themselves about science, so interesting transients, but also about technical details of our platform. So we have a discussion forum that you find here. You can also share links to dedicated events. So if you found an event, of course, you first submit it to Black Hole Tom, but then you may want to discuss it with other colleagues, with other people. You just create one of these deep links, share that, and if they click on it, it opens the app or the website directly at the same event, so you don't have to fiddle with these names and phone numbers and all that. All that is documented again here, including the API at this astro-colibri.science website. If you want, you can also click there. So we try to play with a chatbot. So if you want to talk to our API, you can try this and see what comes out. Community is also, we are running a series of workshops. One was just taking place 10 days ago at the Institut Pascal in Paris-Saclay in France, where we had like 50 people coming together for a week. We tried to split these into a first session on talks and presentations, and then a hackathon where people actually come up with new ideas how to improve either Astro-Colibri or other tools in time domain astrophysics, and we have great ideas coming up that we now have to flesh out over the next weeks and months. You can already, if you're interested, write down the date of the next one. So this is mid-October 25, again, outside Paris in France. And I'll leave you with that slide with a few links. I also have put some flyers outside, so if you don't want to write down all these links, there are QR codes on the back, there on the table next to the Gaia merchandise. Thanks.
Thank you. Questions, comments?
So you mentioned before about the notifications that you can get them on the phone. So I'm not sure if I fully understood. So for example, if there's a new event classified on, so can I make cut so that if someone classified a tidal reception event, for example, on TNS, I will automatically get an alert saying, oh, this one, 80-2024, blah, 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 was newly classified TD, or?
Yes, but you get all other classifications other than supernova as well. So for the moment, we have predefined streams. For classifications, we have one for supernova, one for very bright supernovas, and for everything else. And tidal disruption event would fall into the everything else category. But if there's a lot of interest in only tidal disruption events, we can add another stream saying, okay, this is only tidal disruption events.
I have two questions. So, first question is, do you, like, if a person launches a campaign for example, a gravitational wave object, and they submit their pointings to the traction map?
Yeah.
Oh, that's fantastic. And the second question is, who's like the largest user base from Astro-Colibri? Like, what type of events are like the most popular?
I don't know, because we don't track that.
Oh, okay.
I mean, it all started in the high energy communities. So I'm running the transient program on HESS, high energy gamma ray astronomy, and then we moved into multi-messengers. But I think most of the users are optical astronomers. But I mean, we have a couple of thousand users nowadays. I don't know what everybody's doing.
Okay, any more questions, Martin?
Just a comment on email, because you mentioned that email is completely unsuitable for time-critical communications unless you can accept 2% loss.
I totally agree. That's why we built it. And it doesn't help you. I mean, for example, TNS announces the new transients and the classifications by email, but then you just get a list of new events and you can't do anything with that. So that's why we pass that for you and send you notifications. And then you get all the nice interface.
Okay, I don't see any more questions. Let's thank Fabian again.
Thank you.
And actually, I just want to spend one moment before we move to Josh to show an actual event we've had from Astro Colibri. It will be a good transition to the next talk. So Supernova 2024 GGI, it is Astro Colibri target, and in the comment we say that Fabian has created it. So Fabian must have clicked the button on Astro Colibri, it appeared magically in our system, and then it was observed. And I will show you the beautiful data we got for it. There you go.
Mainly by me.
Yes, and actually the next speaker is the author of most of this data. And that's a very nice transition to Josh's talk. So Josh, if you could share your screen, please. We see your screen, but we don't see your slides.
Can you see my slide now?
Yeah, that's okay. Yeah, you're ready to go.
Okay. So yeah, thank you for giving me the possibility to present my follow-up of Gaia alerts. I know Lukas since 2018, when I first heard about BH Tom. And for those who are not knowing me, I'm a retired nuclear physicist and an amateur astronomer. So I have wrote as an observatory in San Pedro de Atacama. So ROAD stands for Remote Observatory Atacama Desert at the place of Alain Marie. And I last visited San Pedro in 2018. So that was before the pandemic, where it was very touristic with restaurants, hotels, internet, power, and water. So internet is, of course, very important. It's about 2,500 meter elevation. And yeah, as you know, Chile has an exceptional number of clear nights. I'm there since 2011. So the past 30 years, I have observed between 312 and 345 nights. ROAD is equipped with off-the-shelf equipment. So I bought a 40 centimeter f6.8 optimized dial Kirkham from Orion Optics. The mount where it is on is an ASA DDM85 direct drive mount. It's a very fast mount. You will see why this is important. Since last year, May 2023, I have changed the former CCD camera into a CMOS camera from QHY, a Chinese producer, with the previous UBVRI Astrodon photometric filters. And I use standard Windows software, MaximDL, CCD Commander, and Leslie Photometry for automation and photometry of the images which I take. And to access the local PC, I use VNC or AnyDesk. Yeah. ROAD observes nightly, as I mentioned, at least most of the year, about 30 to 50 targets. Mainly, most of them are in snapshots, normally in BVRI filters. I observe two images per filter, just to be sure that the results are good. Then several targets are in time series. Due to the fact that I have a fast mount, I observe actually 3 to 5 stars simultaneously. So hence every few minutes cadence of the stars. And for most of the stars, the period is long enough that there is no real need for very dense observing every minute or so. And of course, if there is a special request from you guys, I also observe solely during several hours your target. This is an aerial view of space ops in Chile. If you can see my mouse, this is the part where the remote telescopes are located, and this is the part where the Alain is showing the tourists the place and the night sky in Chile. So this is my observatory. So it's located in a clamshell dome, because due to the fact that I observe so many targets a night and simultaneously several targets in time series, a dome would have been worn out by now. So it's better to have a clamshell which opens completely, and the telescope can point to any position in the sky. And Lucas already mentioned, I started this year to follow up for the first time for PH-TOM supernovae. So the first one was 2024 GGY. I observed it for more than 130 nights in 3 filters. And you can see here the light curve. You see quite the difference in the different filters. Another one which I followed was 2024 GY. Also there, I observed it for about 100 nights. And also there, the difference in the different colors is obvious. And it's up to you guys to interpret these light curves. As said, I'm just an amateur astronomer, and I do the observations. Not so long ago, Assassin 24 FS was announced about 1 month ago, and it was immediately requested by Lukáš to observe this target in time series. So I started just when it was announced, and I could follow the more or less the peak of the light curve, and since then observe it in 3 filters with a time series of a certain amount of time. Another one, Gaia 24 AZY, was also observed for more than 120 nights. It showed in the very beginning a strong increase in brightness, and then it leveled out, and I observed it till about 1 month ago in also in time series, and since then I observe it in snapshot to see where the baseline level is located. Gaia 23 DPN I also follow since 2023 for more than 250 nights. I could only observe it on the slope of the diminishing of the light curve. I will continue till the target is behind the sun, and then probably will stop. And there are, of course, other targets of Gaia alerts which I observe since more than 100 nights, but which don't really show kind of microlensing features. All of those information is with PH-TOM. And also other targets from 2024, 4 of them I observe since at least 60 nights. Actually 24 AMO was a microlensing event. I just figured out this morning by checking PH-TOM. But I started after the peak was observed by Gaia. And of course, there are other targets of interest to other people. For instance, young stellar objects for the so-called HOIS collaboration, hunting outbursting young stars. I observe since 2019 2 of them, and since 2021 the 3rd one. And you see how those targets are behaving, especially the Gaia 2019 EYY has shown a cadence of outbursts and diminishing and so on, but not in the last observing period. So this has become a very interesting object for the HOIS people. And of course, there are other highlights from Rhodes. During my career as a nuclear scientist, I was always envying people who have nature papers. And now I have 2 nature papers as an amateur astronomer. The first one in 2016 on RSCO, the first white dwarf pulsator. And since last year, in October 2023, on Assassin 21QJ, which was considered to be the first observed a planetary collision of either 2 mini Neptunes or 2 super Earths. And here you see the light curve. Where the object is only observed a part of the time, because it was not announced earlier. Over 400 days or so, there was huge up and down of the light curve, of the amplitude, and then it leveled out. And so it was actually found that the total event lasted about 1,000 days. And you can read it in the Nature paper. And then there are other systems like J1407, a ring system, where it was observed by WASP in 2009. And if it would be in our solar system at the position of Saturn, which has a ring as well, it would be visible during daytime. Another interesting event was the white dwarf 1145, a zombie star, which was also found by Kepler, and has shown drops in light curve. And I observed it for several years, and the data, I mean, all my data actually are with the AVSO. Further observations are on novae, cataclysmic variables, luminous blue variables, error Lyra stars, symperiodic stars, and so on. And most of the papers I had in the meantime, 130 plus with co-authorships, can be found in archive. Just searching for my last name, which is Hamsch. And in conclusion, so as an amateur astronomer, you can really do and contribute to scientific research and participated in alerts and requests for observations, like, for instance, the Gaia alerts and individual researchers' requests. Gives quite a success in getting the paper getting the information published. And in the meantime, I have 130 refereed papers where I am a co-author. And I especially thank to Brzezimek for uploading Rhodes images to BH-DOM, since he's doing that on an automatic way. I upload my data to Google Drive, and he's downloading them and putting into BH-DOM. So thank you very much for your attention, and this is my email address.
Thank you, Josh. Do we have any questions? Nada.
What is the limiting magnitude? I mean, what with the specific exposure time, how faint can you observe?
It was a question about limiting magnitude.
Yeah, how faint can you go?
Yeah, actually, that depends, of course, on the exposure time. Normally, I mean, I have a CRB star, which I follow since several years, which goes up from magnitude 12 to magnitude 20 in B filter. So with 4 minutes, I can detect the magnitude 19-ish about. But normally I don't took that long exposure. So most of the exposure time is between a few seconds and 1 minute, just to keep I mean, being able to observe as many stars as possible during the night, and not overdoing for a couple of stars or giving them too much time, too much night time.
Milena?
Just a comment. Thank you, Josh, for your dedication. Data is great, and all your dedication. It's nice to be reminded, like we as professional astronomers, more and more often don't have so much dedication as you amateur astronomers have. So thank you for reminding us what's the core of astronomy. Thank you very much.
Thank you for your appreciation.
Yeah, I fully agree. I wanted to remind you the statistics I showed yesterday, that Josh is the winner in the number of submitted frames, and so he submits more than LCO altogether. So 25%. Yeah, 25% of all our data. Yeah.
Thank you. Yeah, I'm also the winner for Hoyce.
Very good, very good. But that's the way to go. I think we professionals should learn that, you know, a robotic observatory in a beautiful place, and, you know, then you show that it's possible to cover many science cases with a lot of data, right? Some of the telescopes, I wish they were as productive as your telescope.
Thank you.
Thank you for this.
Yeah.
Okay, thank you, Josh. Let's move on to the last talk. Yeah. Thank you. Zoom completely cuts out the clapping, so people on Zoom cannot hear the clapping, unfortunately.
Yes, I could.
You could, okay. So that's not completely cutting out. Very good.
Yes.
Right, I need to remember about sharing the screen. I will stop this and then share here. And then Elmer will tell us about cataclysmic variables we've heard about already. And that's it. And it's the clicker, right? You know how to use it? Just forward here. Okay?
Okay, thanks very much. Following this morning's talk on BH-TOM and yesterday's request for various observations, I thought I would motivate for observing cataclysmic variables today, and talk about cataclysmic variables in Gaia alerts mostly, but also in other transient surveys like CRTS and so on. I've shown this picture before, and I really like it. That's why I'm showing it again, because it really shows this artist impression, all of the areas where variability can occur in cataclysmic variables. First, you have the white dwarf at the center there, that can pulsate, for example. You have the donor star, which can also pulsate. There can be flares on that star. There's this stream of material coming from the donor star into the accretion disk and hitting the edge of the accretion disk, forming a bright spot. That can, you know, introduce variability into the light curve. As the two stars orbit around each other, you can get eclipses, for example. And then, of course, there's the accretion disk, which is thermally unstable and have outbursts every so often at a rate which is determined by the rate at which material is transferred from the donor star into the disk. And it's these outbursts that make the cataclysmic variables transients in these transient surveys and allow us to discover a lot of them. Because these outbursts are bright. A system can brighten by as much as 5 magnitudes in the space of a day. So it's very bright, and they pop up in these surveys. And they're also quite common in transient surveys. So that's the yellow box at the top there. That's the CVs I want to talk about. And that's about 14% in Gaia alerts. This plot over here shows both the confirmed and the candidate system. So it's maybe not 100% accurate, but it's the candidates and the confirmed systems together in this one plot. So they're fairly common in transient surveys, and it allows for discovering them. While I'm talking about discovery, I'll just talk about the effect of these transient surveys on the known number of systems in known number of cataclysmic variables. So the first CV was discovered in 1855, exactly as a result of these dwarf nova outbursts that I mentioned. That was UGEM. And as a result, these systems are also called UGEM objects. But it took another 41 years before the second one was discovered. You can see SS Cygni there. And it took until the early 1980s before a model was created for what these systems are. A donor star accreting, a white dwarf accreting from a donor star with an accretion disk. That model, you can see, can I move the mouse? Yes. Formed here in 1980. The first real increase in the number of CVs was here when SDSS started. That, of course, is spectroscopic survey and finding a lot of these systems in there. And then you can see that real boom at the end there. That's when all the transient surveys started. Gaia alerts, CTF, CRTS, Assassin, all of these systems have caused a huge increase in the number of known CVs. And that's one of the things we want to explore. So with the follow-up I want to talk about is what we can learn from various types of follow-up in these systems. So if we first look at just the transient survey data, we can look at, for example, the outbursts in the light curve. So there are some systems with a lot of outbursts in there. Others that still have multiple outbursts but fewer. And then there are some systems that only have a single outburst in all of this time. And then systems like this, which have one or more outbursts, but it's only detected in outbursts. It's not detected in quiescence. And we can go to other surveys like SDSS or PanSTARRS that goes deeper into the photometry than the transient surveys and find out what the quiescent magnitude of these systems are. And that's the dotted line I plot here. So we can find out how faint these systems really are from combining the data from different surveys. So this one here at the bottom is detected in SDSS as 19.8 G magnitude. That one at the top there detected at 22.3. So you can if a system has an outburst amplitude of 5 magnitudes and is detected in outburst at 18th or 19th magnitude in Gaia alerts, it means that in effect we can detect systems as faint as 24th magnitude in these systems, and that would make transient surveys so valuable for these systems because they would be almost impossible, I want to say, in detecting it in any similar way. And that is perhaps something we should think about for the future as well. Surveys like LSSD starting up, that'll go very deep, and what we want to follow up from those systems. So again, looking at the transient survey data, what I'm showing here is the number of outbursts in the light curve, like I showed on the previous plots, against the date of discovery for that system. The colors in there are just to guide the eye. It just bins the data into year-long bins so you can see it. And you can see that the ones with the most outbursts in the light curve, this red box here, were discovered earlier on. And then from then on, the number of outbursts declines in the system. Now, this is, of course, a bias, because the more frequent outbursts in your light curve, the easier a system is to detect. You'll see it more often. And that's why we get that slope down in the plot. But the really interesting thing on here is at the bottom here, is that there are so many CVs in there with just a single outburst in the 6 years. So even systems that were discovered in the first year of the survey still have had only one outburst in 6 years. And what that tells us is that these are systems with low accretion rate. The mass transfer rate from the donor star into the accretion disk is low. So the whole, can I call it population from the survey is dominated by CVs with just a single outburst in 6 years. Now if we look at spectroscopy, combine that data with spectroscopy, and we look at how that differs from the systems with lots of outbursts and single outbursts, we can see some examples at the bottom here. A system with many outbursts here, you can see the blue accretion disk and the Balmer emission lines on there, which is quite typical for a CV. And at the bottom here, you see the emission lines, but you also see the broad absorption wings from the white dwarf around those emission lines. So the emission lines are formed in the disk, and those absorption is from the white dwarf itself. And you can only see those when the accretion disk is very faint, when the accretion rate is very low. And that's what this shows you, that in this cumulative plot, you can see the blue line as disk-dominated CVs, and the green lines as ones where the spectrum is dominated by the white dwarf. So we see that was 60% of the white dwarf dominated CVs have had only one outburst in the survey. Okay, so systems with lower accretion rates. Looking at the Gaia alert specifically, until yesterday there were 26,228 alerts, but I've already published a few more this morning, so that number's already gone up. Around 28% of those have been confirmed spectroscopically, and about 8 to 10 of those per week are cataclysmic variables. As I said, this is the largest group of galactic transients in the survey. There are about 2,422 of the CVs in total, and those are ones that I've looked at. That number may be a little bit higher. That was earlier this year that I went through them in detail. 786 are known or spectroscopic confirmed systems, about 32%, and about 50% of them are systems which were discovered first by Gaia rather than any other survey. So something with a Gaia alert name first before it had any other name. 68% of those have entries in Gaia Data Release 3, and 36% of those have only been detected in outbursts, so the quiescent level is not seen in Gaia or in Gaia alerts. I also find this histogram quite interesting. This is the blue ones are the confirmed CVs, the green ones the CV candidates, and it shows how faint these CVs are. You can see it peaks here at between 19 and 21st magnitude. And again, looking forward to something like LSST, which will go deeper, it'll be interesting to see how much fainter they go. And for that, this technique could be quite interesting, and looking at the very deep magnitudes of these systems and how faint they can be. This is a PDF, so my movie doesn't work. So I'm just going to show this on this. And this is moving to the photometry. Because this is a very interesting and very useful technique for measuring the orbital periods of these binaries. Measuring the orbital periods is important because that is a proxy for the age of the systems, for the evolutionary state of the system. When the accretion disk forms, you'll have material swirling around the white dwarf. And if you imagine the donor star moving around the white dwarf like that, the outer edge of the accretion disk starts interacting with the donor star, and the whole of the accretion disk sort of sloshes around. And the stresses in the disk, because of this moving around, the sloshing around of the accretion disk, causes it to brighten and fade as it goes around. And so that causes little brightness peaks in the light curves. And these are known as superhumps. And because it's related to the donor star moving around, it's very close to the orbital period of the binary. And the useful thing is that this happens when the system goes into outburst. It goes into outburst, most of the material flows inward towards the white dwarf, but to conserve angular momentum, some of it flows outwards as well, so the radius of the accretion disk expands. And that's when you get these superhumps. And when the outburst is over, the disk shrinks back. So this phenomenon of superhumps happens exactly when the system is bright, when it's easiest to observe. And that could be a very useful thing for us to follow up on. So this is an example of one of these systems. So this is the Gaia light curve at the top over here. You can see it's a very faint system, around just brighter than 21st magnitude, with very frequent outbursts in the light curve. And that makes it very difficult to measure the orbital period because it is so faint. But fortunately, because these outbursts occur, we can look for superhumps and see if they are in there. But I first had an opportunity to take a spectrum of the system, and I'll show you here at the bottom. These bluish lines here, those are lines of helium. And lines are not very strong, but there's helium lines over here and here. And the green lines over here, that's the wavelengths of hydrogen. And you can see there's nothing there where the hydrogen line should be. So what this system is known as an AMCVN system, a helium cataclysmic variable. Consists only of helium and some metals in the system. And it also means that they are very compact with very short orbital periods. So what I've done, and what other people have done as well, is to look in TESS to see what data is available there. And we were extremely lucky because TESS actually observed one of these actually multiple of these outbursts, because this system is close to the continuous viewing zone for TESS, and so it was observed multiple times in multiple sectors. And you can see over there, these are the superhumps in the binary coming in after the main outburst in the light curve over there. Maybe this also illustrates the dangers of using TESS, and that you have to be a bit careful, because these variability on here, that's actually not from this target. The TESS pixels are huge, they're 21 arcseconds. And so there's a WUMA in the same pixel, and that's actually what's causing this smaller scale variability in there. But you can pick out the superhumps in there, and that gives us a period of 30 minutes for this system, which I think with spectroscopy this would have been very hard to do because it is so faint. So just as a quick conclusion, say transient surveys are a very efficient way of finding the faintest members of the CV population. Future surveys like LSST will find even more of these and fainter systems of these. And so we have to think about how we want to observe these things and make targeted observations of these systems. And in addition to our own follow-up observations and the wonderful work that people like Josh are doing, there's also value in combining the data from different satellites to find some extra data on these surveys. I'll stop there. Thank you.
Questions? Have you added this target, this AMCVN to BHTAL already?
I think I did with the previous meeting we had.
Right,
yeah.
and is there any data?
I've not checked.
Oh, we should check. Okay. Yes.
I have a question.
Okay.
Yeah, Josh.
Yeah.
I mean, are you publishing targets for amateurs which are not magnitude 20, but brighter on BHDOM or on the email information which we get via BHDOM?
It's not on BHDOM yet. The alerts are all just on the Gaia alerts webpage, and on there they have some magnitudes on there. But I can try and add them to BHDOM as well, the brighter ones.
Okay, thank you.
Okay. So this question here.
I would like to ask, I saw that the number increased a lot over the last many years. So what is the expected number of these systems?
That is a good question, and it's a question I don't really have an answer for. And that's one of the goals we have with doing this, to actually determine the space density of these systems. Because the low accretion rate ones with fewer outbursts, those are the ones we'd expect theoretically to dominate the population, but we see fewer of those. So we think that there must be a lot more, they're just harder to detect. And that's why we are trying to follow up these systems with the fewer outbursts, with the low accretion rates, and see how many there really are in the galaxy.
Okay, so these are binaries, right?
Yes.
From theory, we would have a binary fraction that we are aware that the first population, and from that we can infer the number expected.
There is. If there's a paper by Goliath and Nelson, I think it's 2015 if I remember correctly, and where they discuss it. I just can't remember the number off the top of my head now. Yeah.
Do you have some statistics on the dwarf nova discoveries from Gaia alerts on the amplitudes distribution of the outbursts?
I started looking at that, but it's very incomplete. So I'll have to look at that again. So mostly, I think we've seen systems confirmed as cataclysmic variables with 2 magnitude outbursts, and we've also seen ones with 6 magnitude outbursts. But typically, it's about 3 to 5 magnitudes. But we've seen 2 magnitudes, and then of course there are also the magnetic systems, which don't have outbursts as such, but just the high and low states that we also see in there.
I think that in rumour there's going to be just so many of these discovered, and most of them are probably not that interesting. It's the ones that are the high amplitudes, infrequently outbursting, the low end of ones down in the graveyard.
Yes.
That would be really interesting.
Yes. Yeah. And those are the ones we'd want to follow up quickly, because you might not see another outburst for several decades.
The only problem with Gaia alerts and the amplitude statistics is that the cadence is so low that you might not be catching them at the right moment, right?
You mentioned the diversity of intervals between single outbursts, which is obviously due to a change in the accretion rate.
Yes.
Does one understand where that is coming from? Is because the donor is further away, or it's a different type of star, a supergiant versus a normal star? Does one have information on that?
It's to do with the Roche lobe configuration of the system. And so the ones with the fewer outbursts are also the older systems. And so the accretion rate from the donor star is a little bit lower as well. So it's a structure of the star and the Roche lobe configuration that determines that.
Okay, I don't see any more questions. Thank you, Emma.
Thank you very much.
And we are perfectly on time to go for lunch. And we resume at... What time do we resume? We resume at... Well, let's resume at 10 to 2, okay? Because that will let us keep the schedule going. So 10 minutes before 2. And the lunch is served just across the building on the other side of this floor. Okay, it's time to resume. I put Monica in charge, so be aware. And I suggest Monica stays here and all the speakers stand here so we can hear you and see you well. Not to watch the camera.
Big step.
It's very
High
sensitive.
relax. Yes.
So this is the best place to stay because you're being heard and being seen.
Okay, nice.
And I'll just let Monica check.
Isn't that visible? Is this good enough?
Okay, so guys, we are starting. Sorry, I should start here. Okay, we are starting, but Olivares is not online, so we'll start with next talks, and we hope that people will join us in some time. So Andrei will present you the poster. If we can zoom it, maybe Luca, a little bit.
Yeah, it's gonna probably way better.
Just with 2 fingers. Right?
Okay.
Yeah, exactly.
Oh,
Perfect.
Okay, awesome.
You have your 5 minutes.
Yeah.
10 minutes, sorry.
Okay, sure.
Enjoy.
Thank you. Good evening, everyone. I'm honored to be here. This is my first Gaia workshop, and I'm honored to present, briefly talk about my research work. So it's the novel results in correlation and parameter analysis of quark nova. So the main objective of this research was we tried to investigate. We selected a catalog that consists of 653 dwarf nova systems, and we tried to investigate new correlations that can be between parameters in this catalog. Also, additionally, we selected 5 dwarf nova from Gaia alert index and calculated physical light curve and orbital parameters based on test data and AVS-O data, as well as an SSSN data. So basically, like a short background, the previous speakers already talked about dwarf novas and cataclysmic variable and dwarf nova systems. I just wanted to mention that the dwarf nova are more compact systems, and there are 2 main characteristics of the light curve. We have the outburst and the super outburst. So the super outbursts occur, it believes to occur because of the thermal and tidal stabilities of the accretion disk, and it's usually followed by the super hump phenomena, which are basically modulations of the accretion disk. So in this catalog that we selected, we're coming up to the correlation analysis. In this catalog that we selected, there are 653 dwarf nova systems and 26 different parameters, orbital, light curve parameters, and some of the physical parameters. So we set a so-called null hypothesis. To prove or disprove the null hypothesis, we need to calculate the Pearson and Spearman correlation coefficient, as well as conduct t-value, calculate t-value and critical t-value to prove that correlation is reliable or not. So basically on the figure 2 you can see the correlation, so-called correlation matrix, and all of the possible correlations that can occur between the different parameters for these systems. By sorting out correlations and comparing them to previous research, we identified 28 correlations using Pearson correlation coefficient and 32 correlations using Spearman correlation coefficient. And we basically selected, on the figure, on the table 1, you can see 6 key correlations with the highest correlation coefficient, basically. So thus we decided to calculate empirical equations using Bayesian statistics and MCMC linear regression method. As you can see on the figure 3, we have two graph examples. The first one is between the drop duration of the super outburst and the duration of entire outburst. The second correlation is between the Plato phase duration of the super outburst and the entire duration of the super outburst. It's important to mention that actually this research started from just 5 dwarf nova systems that I selected from Gaia alert index, and I tried to calculate physical and orbital parameters using different empirical equations. I successfully calculated some of the physical parameters having just a superhump period at the beginning, and then using empirical equations, I calculated physical parameters. But I soon realized it's not going to work, and it's most important to focus on the larger data sets. Therefore, I conducted the statistical analysis. For example, these red points on the plot are our results, and they match with the results from the correlation analysis. And finally, the summary and outlook. We investigated the catalogs of 653 Farfnova systems. We identified 28 correlated using Pearson and 32 correlation using Spearman correlation coefficients. From these correlations, we selected 6 key correlations. We also calculated physical light curve and orbital parameters based on test data, SSN and AAVSO data. We also, so for the outlook for our research, we're planning to first of all, conduct statistical analysis on the larger data set. Because, for example, for this, we see like a huge gap of data. It would be interesting to find some of that data points there. Secondly, we will separate each dwarf nova type and conduct the statistical analysis for each of dwarf nova type, because for some correlations, they are different for separate dwarf novas, basically. That's pretty much it. Thank you.
Any questions or comments? Remember that he's young and this was a handsome young astronomer. Milena, please.
Yeah, I think the most important is that you are it doesn't matter what age and your answer. I have a question regarding did you analyze all the data together, like from various data sources, or you somehow split it into, like you said, tests and other data? You analyze it all together.
Are you talking about the correlation analysis?
Yes.
So the correlation analysis, we just took the catalog that was already composed, and this catalog was mainly from data of AVSO, SSN, and probably not test data. So I use test data mainly for calculation of physical parameters.
Yeah, but then you put all of them together.
Yes, I've cleaned like the different points that were flying just away, that were meaningless, and I just basically conducted statistical all together.
Karolina, please.
2 questions. You mentioned that you used the catalog. Which one?
So it's from this.
Okay. And the equation for the formula for the epsilon was also taken from the paper, or this is a new estimation?
It was taken from the paper, from this one.
Okay. So I just have a comment. That makes sense.
Thank you.
Anybody else? No? So thank you, Andrea. And now our third speaker, but second, Mira, please.
Down.
Just press here.
Press here. Okay. I'd like to present some results of our photometric and colorimetric studies of selected target objects. We use mainly our own observations, which we have performed at our observatories at Terskol and and Lesniki near Kyiv. We selected unclassified objects in order to try to classify them. There are photometric observations using BVRI filters. Okay.
Working.
The first object I like to present is Gaia 19FDX. This transient was observed by Gaia, but on the Gaia page we have only 3 points of observations and nothing more. We start our observations just after this alert was published. 5 nights at telescope and 5 nights at the Crimea Astrophysical Observatory. I will tell about later. So we uploaded all our follow-up data points to the Cambridge Photometric Calibration Server, and you can see here a screenshot of the page, and our observations were there. Taking into account a sudden decrease, a sudden increase and then a small decrease and then rapid decay after 20 days later, we suggested that this object can be a cataclysmic variable star. This here. Okay. So this object was also observed at the Crimea Astrophysical Observatory. There was observation only using a clear filter, but these observations allowed us to determine period. And if we look at our observations and a decay in December, so we can say that Gaia Gaia 19FDX faded from the super outburst between December 2 and 5. What was interesting, we additionally found this transient event in the Sonnenberg astroplates and measured the magnitudes. It was in 1982, and the magnitudes here you can see. And my question to you, can you include this measurement in brainstorm? Okay. Now, what we have now at the H-Tom page. Here, not too much observations, only from ZTF, and our observations are absent. They should be in the SERP. So we have searched for additional observations in other database, and we used Assassin database and more complete observations from ZTF. In order to determine what type of cataclysmic variables we have, we needed a long and detailed light curve. And we have now this light curve, and we can see that the combination of automatic data results in a detailed light curve coverage that allowed us to say that this object is a cataclysm variable of SU Uma majoris type. Here you can see some results of our investigations, and the next object is quasar PKS 1222. We focus here on an outburst which was observed in March, April 22 at the Tesco Observatory. We have performed not too much observations, but these observations allowed us to find color indices of the object and to make some conclusions about the behavior of this object. Here, conclusions, results of our analysis. And what is about BH tone? I should say that here, light curve for this object is perfect. And we can now, and for this object, we can use this light curve to further investigate the behavior of the object. So, our conclusions, combination of data allowed us to better identify the highly variable features of selected transient events. Here was example of Gaia 19 FTX, and we make use of pH tone because it provides synergy of a very ground-based and grounded space-based observations that allow us to improve our analysis. So, thank you for attention.
Really nice work. Any questions or comments? Nada, please.
Would spectroscopy follow up during different?
Follow up for Gaia?
Sorry. I was thinking about the first object that you
that was.
I think it was DRX.
DFX. DFX, I think.
Sorry, yeah.
Spectroscopy, if we look at the light curve, so we can see that it's a find object.
Yes, because I was checking because it looks like a hostless transient. So did you try to obtain spectrum for this to see what it was?
Not yet.
It's quite a good idea to make some.
It
will be. Yeah. So, any more comments? Questions? Okay.
I'll just comment that the photometric plates is very easy to add. So maybe you have more data like this we could add.
The old one.
Yeah, the photographic plates. It would be really good to include them as well.
We can find more.
Very good. Very good.
Find and sell. Okay. Perfect. Thank you very much. Sorry. Sorry, please.
For this event, there's also a bit of data in Atlas that you might want to.
Atlas. Okay.
I'm not sure it's very helpful, but
our work is ongoing, so we can use. Thank you for your comment.
So next year you will show us further observations. Karolina?
I have a question related to what do you plan to scan the photographic plates to make it accessible on internet, the photographic plates?
No, those plates are physical at the Sonnenberg Observatory Museum now. And our colleague Sergei Shularov from Slovakia, he was here and found. So no digital plates for this object.
Anything more? Okay, thank you very much. And our next speaker is Barbara Jakinczyk from Toruń. Young student, first talk will be gently for her.
Okay, it is lesson. Działa? Chyba? Mam nadzieję. Okay. Hello everyone. My name is Barbara Jakinczyk and I came here from Nicolaus Copernicus University in Toruń. And I want to show you what I work on for my bachelor's degree. I am just starting my third year of bachelor's degree and I work with Dr. Karolina Wąkowska. So first of all, the star that I'm working on is a polar. Polars are a subclass of cataclysmic variables. It's a system where the white dwarf has a very strong magnetic field. So the accretion, the whole accretion process depends on the magnetic field. Here I found a sketch of my star in one of the papers, which represents quite well how polars work. So when the mass is falling from the donor, at the very beginning, the kinetic energy is greater than the magnetic field, so it falls as the kinetic energy says. But when it gets closer to the white dwarf that is in here, the magnetic field starts to dictate the flow. So the mass is falling along the magnetic field lines. Okay, something about my star. So AR Uma was first discovered in the 1960s as a variable star that has 14.5 to 16 magnitude range. Here is a CCD frame from our telescope. Is this object in here? In this table, I put some parameters of the star if someone is interested. I want you to keep in mind the orbital period value because I will be referencing to that later. Okay, AFSO stands for American Association Variable Star Observers. It was first founded in 1911 as a source of amateur observations for Harvard College University astronomers. And basically it gives you access to amateurs observations data for worldwide access. They also archive the data they collect. Here on the chart, I generated it on a AFSO website for around 25 years of ARUMA monitoring. As you can see, it is mostly in the low state. Not much is happening, but recently there was a big event happening, and I will be referencing to that. So this is the zoomed-in peak that was in the previous chart. This is May 2023, so last year. I highlighted here the 4 nights that are marked in here because we were observing them in our own observatory. We had a little campaign with our 60-centimeter Cassegrain telescope. It was quite important for us because it was one of the first kind of campaigns after our telescope was recoated. So I matched our data, which is the black dots, to AFSO data that was on previous chart for the 4 nights. And it fits quite well, so we know that our telescope works fine. Our mirror, our camera, everything is okay, and that's a great information for us. Here are zoomed in, the 4 nights zoomed in, so the black dots again are our data, and the green ones are from AFSA. Okay, here I have also TESS data. TESS observed Air UMA in 2 sectors. In sector number 22, which is the top chart, it is 2020 February to March, and sector number 48 2 years later, in 2022 January to February. Because in both of those sectors there is a gap in the data, I decided to treat the data sets as 4, not 2. At the very first sight, it looks quite noisy, but I decided to zoom in for 1 night from each data set. And here we can see that actually it's some periodical variations. So we decided to calculate periodograms from the data. So here are all periodograms that I calculated. The left side top one is from our Piwnice data, and the left bottom one is from AFSO. I calculated the orbital period, and the values are here, which correspond to the values that I found in literature that I showed you at the very beginning. At the right side, I have periodograms calculated from TESS data for each sector for 2 parts. And as you can see, it is clearly way better quality data than ours, well, because we have only 4 nights and we were doing observations from the ground, and TESS is around a month of continuous observation, so it's definitely better. And that's basically, for the moment, the only thing we calculated, because there was a paper published recently that works on the TESS data for this object and basically covers everything that can be calculated. So there is not much for us left to do. Here is the chart from the paper that you could also see on yesterday's Carolina talk. Here also we have around 20 years of ARUMA monitoring. And those 2 peaks on AFSO, we could see 3 peaks before, so something is missing here. Again, mostly low state, and a big peak in May 2023. And what we want to do now is to try to observe, try to apply for EVN for Air UMA, so we could get some radio data, so we could analyze radio and optical wavelength together. But what we need is, when we get the EVN time, we need to have high quality photometric data, so we could compare them what's happening in both of the wavelengths. And TESS is not gonna observe the star anymore, and AFSO data can be inconsistent. So that's why we would like to establish a BH-TOM campaign when we will get the EVN time. So for now, we don't need the observations. But when we get the EVN time, it will be very crucial for us to get as much data as we can, so we could compare if there's some correlation between what's happening in the radio wavelength and in the optical wavelength. So a while ago, I created a UMA target in BH-TOM. And yeah, when we will get the EVN time, we will be texting you, I guess. Thank you for your time.
Thank you. Please.
I think the first thing what you can see here is that you have more data than they have in data, right?
Yes.
So you have additional outputs in linear, they haven't used linear, right? You have Atlas, they haven't used Atlas. And you have NeoWise, they haven't used NeoWise. So I would still consider you, that you consider writing a paper by yourself again. Yeah, well, you have some, it's an independent analysis, and it's still worth it.
Only test data, because they focus on test data. Even they showed that 20 years later, they only use virtual parts, but we definitely use this.
Yeah, so all the work you've invested, it's worth showing again, and then you can use this data differently. One more comment, because you mentioned you want to you will be texting people advertising the campaign.
Yes.
At the moment, the best way to do it is the Bridgestone newsletter.
Yes.
Because people are signed in to this, and it's an open mailing list, right? So feel free, that's common to everyone. If you want to have your particular target to be observed, it's not enough sometimes to put it in the system. The robots will notice it, right? But humans might not, because there's many other targets. So humans prefer to get a personal email. So I strongly encourage, and some people were doing it, if you have something interesting now, you would like to describe your campaign, write it in an email on the Bridgestone newsletter. The link is on the About, under the About page. You write, you want to observe for 1 year, in these bands, how frequently, give some details. And then also people, that helps the observers to know whom to contact, that they've been having some issues, or maybe there's a person behind it, right? So don't forget about this, and definitely this is what you should do.
Okay, thank you.
That's a great idea.
I have a comment.
Wait a moment. There is a queue.
Funnily enough, I was looking at this data when we were doing our exercise this morning, and I clicked on the download radiate data, and there was nothing there.
Nothing there.
So my question is, has it been detected as a radio source?
Yes, it was.
It has. So
it was first
detected by the VLA, was it?
It was first detected as a radio source, and then it was matched that the radio source is this object.
Yes.
Do you remember?
In photometry.
Radio telescope?
There was a campaign that Paul Barrett did on many polars using the VLA. I know he detected quite a lot of them with longer observations. In the initial study where they just did snapshots, he hardly got anything because it's very orbitally modulated, the radio emission.
Well, if it would be detected by VLA within fields survey, then we should get a point here.
Yeah.
We don't see it, so probably it was a survey that which is not implemented in the shop yet. We have access to fields survey and local.
Right. Well, that's another issue, is that we've done a similar survey of polars with Meerkat at low frequency. We haven't detected any. So there's a tension here between low and high frequency.
Josh, now your turn, please.
Yeah. Although you mentioned that the AVSO might not be consistent, I would recommend to ask an AVSO alert if you have your radio observations, because as you have seen, the AVSO has a long constancy in this observations of this target. So any additional observation, I think, is helpful.
Okay, thank you.
Thank you, Josh. Any more comments? Milena, please.
Would you use to calculate areograms? And also, what's the other, there's a peak areogram of another reference? What's that?
So I used period 04 program, sorry, and yes, this second peak is the harmonica from the orbital period, the second harmonica.
Okay. Any comments? Questions more? No? So thank you very much, Barbara. And now second student from Toruń, Mateusz Motyliński. Again about variable stars. I like those stars. As well. Yeah, Barbara starts out, so we are perfectly happy.
Okay, stand here.
Okay, so hello everyone. I'm Mateusz Motyliński from the Nicolaus Copernicus University, and today I will get you a short talk about my master thesis, which is supervised by Carolina as well. And my talk is about SW Sextantis type based on photometric observation from the TESS satellites. So, at the beginning, here we have the classification feature from the US Springer's book of the family of the accretion white dwarfs. And we have SW Sextantis stars here. It's classified as the non-magnetic systems and novel-likes variables. However, in some literature or publication, the SW sex is classified as a separately class of stars, not like novel-like variables, but in this talk I will assume the SW Sextantis is the part of the novel-likes family. So, few words about novel-likes variables. It's part of the cataclysmic stars. This is the binary system with the white dwarf as a main component with the accretion disk, and the donor star. And this system is we have the very high transfer mass between these two components. So in the light curves we don't see any regular outburst like with the dwarf novae on the recurrent novae, because it's basically in the permanent outburst. So his light curves is bright and have more or less steady luminosity. And we classification have the three types of these stars. First one is the UX Ursa Majoris, which have the very steady and very bright accretion disk. Second one is VY Sculptoris, which have the sometimes enter to the low states due to the have the temporary dimming of all systems in the light curves. And the last one is my SW sex. So their characteristics is almost all of it have the deep eclipses of the white dwarf, and also their orbital periods is above 3 hours, and display some features in their spectra, including the helium emission. And here we have the example of the radial velocity, the light curve, and some the spectroscopy for example of this SW Sextantis stars. So at the moment the people classified over the 30 stars as this type. So I will choose some of it with the deepest eclipses, and also this one which have the test sectors. So I was analyzed almost 30 sectors from the test data for 13 stars. And here there are examples for AC Cancri and Pake Sand. And you may wonder why AC Cancri have the beautiful light curve compared to the extent, and this is because AC concrete sectors was grouped together, so it's one after each other. So it's like we have here 3 sectors, like 34, 35, 36, but for PXN we have the gap between sectors almost 3 here. So next steps of my analysis was to create the periodograms. It was also calculated with the programs called Period 04, and here we have the examples of few sectors for few stars I was calculate, and we can see for each star is a strong signal from the orbital period, and in some case, like for this example, we have a little bit smaller signal, but which is not from the orbital period, but I will call it later, so wait a few seconds. And here we have orbital periods collected in the table compared to the periods from the literature, and this value is consistent. So in last and 2 years before, there were 2 papers which are analyze the orbital period for this type of stars. So we decided with Carolina to not focus on this part of analysis, and we will try to do analysis with more interesting features of the stars. So the first one is permanent superhumps, and for the dwarf novae, we can there was 2 types of superhumps, like the positive and negative ones, but for the nova-like variables like SW6 with the longer orbital period than dwarf novae, we have the something like called the permanent superhumps, and this is the paper from this year, which have the analysis the feature for the permanent superhumps of one of the stars. And as you can see, we have the periodogram, which have here is the signal from the orbital period, and here is another signal which is from the superhumps, and we have also seen that on these 2 figures, and this is kind of the mystery behind the behavior of this feature from what happened here. We don't exactly know, so this is still in debate. So we try to do similar analysis for our stars, and the second part of my analysis is correlated with the thermal cycle. This is a schematic figure from the schematic cycle for the also dwarf novae. So this is the dependencies of the effective temperature and the dense of the accretion disk, and how the gas is ionized within that accretion disk. So for the nova-like variables like SW6, we have that in the top of this figure, because the mass transfer is that high, so we still have very ionized accretion disk. But sometimes, here, this is the example of, we have here the stars and we put the data from TESS and from AFSO. So we get here a drop of the brightness, and it's a very interesting feature from the stars when they have sometimes drop their mass transfer for a few months or something like that, and back to his normal status. But more interesting example I have in the last slide, because here is the Pake's end, and here we are very lucky because the test data is in the same time as the drop of the brightness. So our next steps of the analysis will be to study this drop of the brightness for these stars which have it in the AFSO. Yeah, this was two parts of this study, and we will probably try to also check if it's possible to observe the stars with the radio observation, but it was still in the consideration of our work. So yeah, that's all from my side. Thank you very much.
So, any questions, comments? Mila, you were first.
To ask about the period of EW, because there was a difference in 1 hour. Is it a typo or was it really detected? I mean, you showed the table periods, and it's the first one on the right after that. See, there's 3 and there's 2. Is it a typo or
This probably the error with my when I'm this probably was the 3.27. So yeah, this was a little mistake.
No, but I just wanted to be.
Yeah.
That was my expected that.
Okay. Of course.
This very last target that you show, the light curves, the one that you nicely, this one. If you take a look at only on the test data, do you see like any special features in the time of the plot, or is it nothing really unexpected?
Well, when we zoom it, it was very similar to this another sector which is not in this kind of drop, but we see some when we get higher, but the amplitude of the eclipses is pretty the same. So,
David, please.
So it looks like it's quite a wide, so that dip has lasted for weeks, right? Was there any chance of getting spectroscopy of that source at the time? You know, if anyone did, or was this data too late to know to react quickly?
Exactly that drop of the brightness for Pake's end, it was in 2019, so maybe someone did it, but I'm not sure.
2019.
Yeah, 2019.
So this is a VY Sculptoris system. Is that what you think? You know, these nodalites that sometimes have dips, but I don't think they've ever been seen in SW6 studies before, have they?
Yeah, well, when I search the literature for this type of the stars, I don't have any information for the drop of the brightness for this type of stars, so it's quite interesting thing.
Yeah. And the other thing I'm struck by is that dynamical power spectrum. If you can go back to that. So you have like 6.5 cycles per day and 7. Yeah, the next one. No, the trailed one, the one you had. Go back. The other way.
Oh, yeah. Okay.
That one.
Okay.
Yeah. So it looks to me like that less, lower amplitude signal seems to have some structure to it. Would you agree?
Yeah.
It's sort of wandering up and down in frequency.
That's why we want to focus on this analysis. What Mateusz managed to do is that he, right now, because it's like almost 2,000 of stars, he just overlapped AAPSO and test data. But the next step for us is to put these stars together to acquire all possible data and investigate them together, especially that, as you mentioned, is the fact that nobody focused thoroughly on the drops when the stars are in the low state, and also this kind of analysis that we have additional frequencies related to permanent supernovas.
There is at least one target in the Ipsum already, the 1515 at Chile. Not here, this one. And there is a lot of atlas data and a bunch of data from made by Liam Hardy from camera dimensions, 60 centimeters also. So we have some.
That's nice.
So definitely further.
Okay. Any more questions or comments for a young student? No? So thank you, Mateusz, very much. And right now, we will have online lecture. Then Goa, he's online.
He is.
So we will try to switch on the presentation.
Hi, can you share your screen, please?
Yeah, I'm trying. Give me a moment. Can you see the slide?
Yes.
Yes.
Okay, perfect.
Yes.
We have.
You're ready to go.
Floor is yours.
Hi, good afternoon, everybody. First of all, I want to thank the organizer to give me this opportunity to present online. I'm sorry that I cannot join you together in Greece, but it's a good opportunity for us to show what we are doing now. So today I'm going to present our work about eruptive young-cell objects from the large-scale survey era. I'm Jen. I'm currently a faculty member in the Universidad de Valparaíso in Chile, and most of this work has been done in collaboration between Chile and Europe. So let's start. First of all, the mass accretion event is a universal process, and today we just heard about the mass accretion on binaries. And then I'm going to show you different scales of the mass accretion through the accretion disk. So
excuse me, if you're changing slides, we don't see any changes in slides.
No, sorry. This happens before. So let me quit the presentation and come back again, right? Sorry about that. Okay, it seems like I need to share the entire desktop.
Yes, precisely.
Probably that's the better option. Right. Can you see my second slide?
Yes, that's better. Yes, thank you.
Right. Thank you, guys. Thank you for reminding me. So yeah, so today we heard about binaries, and then this accretion disk we detected around AGNs, around binaries, and around young stars, and even young planet. So the mass accretion actually link from one of the biggest astronomy body to the smallest astronomical body. And today we're going to talk about accretions on young stars. Since most of you are not familiar with the young-cell objects, here is a brief introduction. On the left-hand side, you can see a sketch from an artist in Chile. So she showed us, there's a central star here, and then around the star, there is a protoplanetary disk, or we call them the circumstellar disk. There are a lot of planets formation going on, and you can see the gaps and rings around this disk caused by the accretion of the planet. And also at the innermost of the accretion disk, which is less than 0.1 AU, we have the accretion from the disk to the star. In the innermost of the accretion disk, this accretion is actually controlled by the stellar magnetic field. And the material accreted onto the star to form this accretion shock, and then we can observe this mass accretion in optical, in UV, and in the infrared. However, this kind of accretion is not steady. This comes to our photometric analysis. So we have two types of accretion variability on those young stars. One type is the routine variability that, these young stars are changing their brightness in a small scale all the time. And then on the other hand, we have the outburst. This outburst contains the enhancement of the accretion rate of 1 to 2 or even more orders of magnitude, and then can last for several hundred days to several years, and then to several decades. So here is another very nice summary chart provided by Lynn Hillenbrand that summarized the variable events on young stellar objects. The x-axis is the duration of the event, and then the y-axis is the optical amplitude. And today we're going to focus on accretion, which is in the blue. And you can see the accretion-related variability can last from 1 day to several decades. And Gaia in here, so using the Gaia time series, we can analyze this kind of variability on time scale of weeks to 1 decade. So it helps us to find those events and to analyze the details of this accretion burst on young stars. So let's come back to the motivation. Why do we want to study the accretion burst? First of all, it matters because it contributes a lot to the stellar mass assembly. From the theoretical analysis, we know that actually more than 50% of the stellar mass is actually gathered during this high accretion rate stage. We also know that, there are star disk and planet interactions happening at the innermost of the accretion disk, and whether this accretion burst is caused by perturbation from a young planet, and how will this accretion burst feedback to the planet formation at the innermost of the disk. The latest, we want to know the physical mechanisms that caused this accretion burst, whether it's coming from extra mass inject into the system, or it caused by another gravitational body in the system, or it caused by the instability inside the accretion disk. So there are a lot of questions to be answered. As an observer, my research interest is to find those eruptive young stellar objects through the large-scale surveys, because these events are relatively rare compared to the routine variability. So actually, we can detect about 10 to -4 per star per year of this event. To detect more of this event, we need to use large-scale surveys. And so far, there are 3 surveys which contribute a lot to our research, including Gaia Science Alert, and VVV survey in the near-infrared, and NEO-WISE survey in the mid-infrared. Here, I'm showing you an SED of the young stars before and after the outburst. You can see that the dramatic change on the flux of this event from optical to infrared. And then we also want to catch the full duration of the event, so we need a long-lasting light curve. We also want to detect the earlier evolutionary stage, because around the earlier stage of the star formation, the stars still have a large disk, which has a larger instability inside the disk. Our team, working with the VV survey data, has been working really hard to detect those eruptive white zones. So far, we're able to find hundreds of eruptive white zones from the VV survey data. Our methods, including to deliver the photometric catalog to the community, and then we obtain spectroscopy follow-up observations using Chilean-based telescopes. And then the third step is to study individual variable vessels, which has novel features or they have highest amplitude we can find. Although, today is a workshop about Gaia. So let's talk about Gaia-discovered eruptive vessels. Here is one case that we're working on. So it's L22278. It has one of the highest amplitude outbursts we detected on a low mass star. And if you can focus on the yellow color here, so this is the light curve from Gaia. So before the outburst, this star didn't have the flux in Gaia, so we have a lower limit here. And then it went to an outburst with a larger than 7 magnitude in Gaia. And after the initial outburst, we see some decaying and then gradually returned back to the photometric maximum. We also captured this event using VVV survey in the near infrared and the NEO-WISE in the mid infrared, and we can describe the rising stage of this event using these 3 wavelengths. We found some delay between the infrared and the Gaia light curve here, suggesting that the instability is originated from the inner disk instead of originated directly from the star. So the disk start to heat up first, and then the instability reach the star and then create this outburst observed by Gaia. So we have another field works, which is ongoing to follow up of Gaia alert on young stars. One of them, again, is a combination of the Gaia data, VV data, and WISE data. In 2014, we captured an EX-ray type outburst on a young star using VVV and WISE. After that, we see that Gaia launched in 2015, and then we have the fading stage of this outburst captured by Gaia. However, more recently, in early 2024, we have another alert from Gaia telling us this object is going back to outburst again. We also use Atlas data to close monitoring this event on a weekly basis. Even until last week, we can still see the last data points here. So the star is still relatively bright in a outbursting stage. After the triggering of Gaia alert, we started to have spectroscopy follow-up observations of this event. And you can see we have been obtained several spectra during the outbursting stage. From the spectroscopy analysis, we confirm that this is, again, this is a young star and the mass accretion rate is enhancing during the outburst. And this is collaborating with Mike from Hertfordshire University. Another work we were doing is led by a student called Koshavinder Singh. He's a PhD candidate in Tata Institute in India. It is another ongoing EX-ray type outburst captured by Gaia, ZTF, and Assassin. This is actually the light curve I show you in the introduction. So you can see the routine variability again and the outburst back in 2019. And earlier this year, the star went into outburst again and triggered the Gaia alert. After we received the Gaia alert, our team has been using larger telescope spectroscopy observations around the world to follow up this event, including the data from X-shooter VLT through a DDT observation. And then we can see the dramatic change from the quiescent spectra shown in the red here. We were taken in 2019. And then the latest spectrum we took on VLT that has a lot of emission lines. And then also we see the double peaks, the emission features suggesting the faster rotating of the inner accretion disk. We also obtained more spectra from telescopes in Chile, in South Africa, and in India. So this is really an international team working on to follow up these events. In the last, I want to show you something about our future plans. So the alert system has been giving us numerous of eruptive event, whether on stars or on galaxies. But in the future, we will have Rubin data. And to analyze Rubin data, we need machine learning-based community brokers. So one of the broker we are participating in is the Alersi broker, which is the official Chilean broker for the Rubin data. In the future, we want to inject more emphasis on the young stellar objects to detect the variability of young stars. And we are also on the stage that we have enough outbursts observed, so we want to analyze the reoccurrence rate and to do more statistical analysis of this event, and utilizing the watch list function that there are thousands of young stars, and then you are watching the outburst among those young stars and give you a better parent sample that you can do analysis. And then we want to using the fast follow-up observations, especially using the target of opportunity mode of the observations. We can do the detections from UV all the way to the sub-millimeter. And here's the example of the ALMA observation of one of the eruptive young stellar objects. So yeah, I'm finishing here. This is my take-home messages. Accretion burst on young stars can tell us some details about the stellar mass assembly and planet formation. And large-scale surveys are powerful to detect those eruptive young stars. We need to use spectroscopy observations to do fast follow-up observations to analyze the accretion rate change on those events. And we are on the stage to study from individual objects to statistical samples. Here, I show you 10 light curves actually obtained by Gaia in the past few years, and all of them are classified as accretion burst on young stars. So thank you so much, and I'm looking forward to the questions.
Okay, thank you, sir. Any questions or comments? Simon, you were first. Nie ty.
Sorry, przepraszam.
Simon.
Sorry, because I wanted to say hi to Shen, but Simon was first. But Simon was first, yeah, please.
Okay, I'll jump in very quickly. Mine's, I don't know if you can see me, really good work. I'm really impressed with what you guys are doing. My question is, I think it was L278.
Yeah.
And you were able to translate that it began in WISE, the event, even though it's detected in the optical. So I wonder, using the WISE colors, if you can see if it actually started further out in the disk, if you can put some temperature constraint on the region that went into outburst first.
This is a very good question, actually, where we tried to fit the temperature profile of the SED, and it's a little bit difficult because error bars, you can see
error bars,
is large, but our only constraint is around 0.1 AU, something like that.
Okay,
yeah.
Okay, thank you.
Thank you.
Sorry, Melinda.
I have a question.
So, Zhao, I was wondering actually with the same slide, you mentioned the delay between infrared and visual data. Can you see any type of delay or color changes in terms of BP and RP data? Or are they too close to each other in terms of the wavelength? Or
that's an important question, actually. Unfortunately, we didn't have the BP and RP during the initiate first several epochs because it's too faint for BP.
Okay.
But then we do see the color change after the outburst, and then you can see here the GP, RP, and then we can fit it with a perfectly extinction track. So actually, this change is caused by the extinction. And then there is an immediate extinction rise, like a cloud is rising after the outburst. And then after a few years, this extinction is clearing out, and then we see the re-brightening of this event.
Yeah, but it's very nice usage of various like filters of Gaia, so that's cool. Awesome. Yeah, thank you. Nice work.
Okay, thank you. Michelle, you have... Josh was first. Okay, so Josh.
Hey, hi. This is Josh Hamsch. I gave a presentation this morning. I am participating in HOIS, hunting outbursting young stellar objects. So like you do. I have a telescope in Chile as well. and I could provide BVI and R color information. I mean, I got your email address. I will send you an email, and maybe we can continue by email. So I'm open for collaborations.
Absolutely, thank you so much, George. I'm sorry that I missed the morning session because it's we have 6 hours time difference.
Yeah, no problem. Yeah, my telescope was working this morning. Yeah. Okay.
Remember then that you can always watch it on our YouTube, so
yes,
you can catch up with lectures.
I will rewatch the talks.
Yeah.
Thank you.
Thank you.
Okay, Michelle, please your question.
My question is perhaps more for Simon, because often in Gaia alerts you see candidate young stellar objects. On what are you basing your comment? Because it's not the light curve which can say that. Is it the BPR, etc.?
Sorry, can you get slightly closer to the computer because I cannot hear you.
I didn't introduce myself. I'm Simon Hodgkin. The question was from Michel Dennefeld and asked me why, I think I understood, why on the Gaia alerts page we flagged it as a non-stellar object.
Yeah, you say YSO candidate. On what are you basing this comment?
Why did I call it a YSO candidate? Because we cross-match against all the catalogs of known YSOs provided for us by Concoli team, thank you very much, and also the Spicy catalog, which is from Mike Kuhn, I think, if I remember correctly. And and so we do a cross-match against these, and if it's in one of these catalogs, if it says candidate, we put it as a candidate. If it's confirmed YSO, then we say it's confirmed YSO. Sorry for jumping in and answering your question.
Yeah, this is correct. And also, for some of the eruptive YSOs, because they were too faint before the outburst, so it's difficult to classify as their YSOs. But after the outburst, when we took the spectroscopy observations, we confirmed it's YSOs, so it happened sometime.
Okay. Any more questions, comments? And no? Okay, so thank you very much then.
So I'm still waiting for the for the presentation of Andrea.
Yeah, we have one more presentation before coffee break. But we have some big presentation which has problems to come to us.
In the meantime, I will make one announcement. So before you go to coffee, let's meet outside at these curvy stairs and have a workshop picture taken, okay? That's a good idea. The presentation is coming. Andrea, you can start. I need to start sharing the screen.
Andrea, say a few words about you before we start. You can dance, make some performance.
I would like to thank the organizers for inviting me and to giving me this opportunity to present our work. And I apologize for this mess up. It's all my fault.
What's the name again? I need to remember to share the screen. Almost there. Very good.
Perfect. Floor is yours.
Where do I? Okay, my apologies. So I'm going to present the work which we did under the European Space Agency PRODEX project called Gaia Astrometric Microlensing Events, or in short, GAME.
It's all right. You need to watch yourself.
Thank you.
You just need to move it.
Okay, well, thank you. So this is the team that is working on it. So it's a joint project between University of Nova Gorica in Slovenia and Warsaw University in Poland. Some people are here in the audience that you may recognize. As you know, space-time is curved by masses which are in the universe, and they deflect. And this curvature deflects the light and causes what we call microlensing events. So we can get several images, multiple images, and also magnification. So due to the higher number of images, and the increased surface, we will get magnification. So this is called photometric microlensing event. And at the same time, even if we cannot resolve these images, the centroid of the light shifts. It moves like it's shown here in this nice animation by Chris Rybicki. So this was shown in the units of Einstein radius, and lens was stationary. So in fact, everything in the sky moves. So we have a single source would move due to the annual parallax. It would make ellipses, and then we have proper motions of stars, nearby stars, and this causes in these wiggles that we also noticed in this animation before. So this would be the path of a single star, but if we have a microlensing event, of course, there will be additional, let's say, wiggles around that. So here we have the nice animation simulation showing how the centroid of the light shifts due to the motion of, now of course in the sky, both are moving, lens and source are moving, and here we saw how the centroid of the light is moving. Assuming that we have no blending, so that the lens is dark, and here we see in the units, it is in micro arc seconds order of magnitude. So we have many photometric microlensing events detected already. Astrometric microlensing events are more difficult to detect because we have to have very accurate astrometry. So Gaia is good in that, so Gaia can provide this. We see here in this graph on the left that in DR2, for example, that this accuracy, astrometric accuracy was below already 1 milliarc second, but in Gaia DR3 it's even better, and we are expecting DR4 full data in the near future. So Gaia can detect the astrometric microlensing events. There will be also several simulations which predicted the number of such events. But in this project, we asked ourselves, how could we detect when the astrometric time series from Gaia will be known? Will it be able to detect these events and also determine the parameters, microlensing parameters which are behind that? So we decided to do our work based only on astrometry, without any information from photometric time series. So we had to solve a problem of fitting 11 parameters, so 5 are from single source. So as I mentioned, parallax, proper motion of stars, so in a ascension and declination, and of course the position of the source, right ascension and declination. So these are 5 single source parameters, as we call them. And then there are also 6 microlensing parameters, so it is the Einstein radius, the Einstein time, then it is the impact parameter, the distance of the closest approach of the source and lens, U0, time of this closest approach, T0, and then we have 2 components of the microlensing parallax vector, eastern and northern. So this is what we would like to determine from the time series from Gaia. So how does Gaia measure the positions in the sky? Let's say that we have this curve, how the source is wiggling around with respect to some initial right ascension and declination. Of course, Gaia scans the sky and observes at particular times this position. These are the stars in this picture. Gaia then determines the position along the scan direction. So if we look at these gray arrows, so these are actually shift vectors, so in which direction the object moved. But we cannot measure exactly this direction because Gaia only scans in one direction. So we can only measure the projected shift vectors projected on the, along the scan direction. So what we get from an object, from these 4 points, let's say, measured here, is this a time series of this along shifts like shown here. So it is not exactly that we would see the position in the sky like this, but we have a little bit more way to go. So this green dotted curve shows a single source track due to an parallax and proper motion. And then here we simulated also the microlensing track and how it would be seen by Gaia. So we used Astromet and Jagstromet for these simulations, also in the next slide that I will talk about. So these blue lines are trying to show the direction of the scanning of Gaia in these particular points. So what we get from Gaia is this x-ops. So these are as a function of time, what were these projected shifts along the scanning direction. So if we then make a fit on this with this single source 5 parameters, then we get the difference between the single source and what is the difference between the green and this other microlensing track here. So this was as a function of time. So this is then what we would get from Gaia, these two. So now we ask ourselves, okay, let's say we can simulate this, what we get from Gaia, and then we can ask ourselves, can we from this determine what were the parameters that went into this simulation? So for this we developed this code that we call game filter. So it works on the generated mock microlensing events from Gaia. It reads in this observational data that we saw in previous two plots. And then it chooses a specific single source and microlensing parameters. It calculates the predicted data, so what would be the x fit in this case, and then it calculates this value, which we called move, which is just basically measures the goodness of the fit. And here number n is the number of observations or Gaia visits on this field. So we want to minimize this in order to get the best fit that is possible. We are using this limited memory Broyden-Fletcher-Goldfarb Shano 8 algorithm to explore the parameter space and determine the optimal parameters. So we chose this because it provided the best results, the best accuracy, as we will see. So we also helped this algorithm by providing some initial guesses for parameters. So for 5 single source parameters, we used guesses from the single source fit without any microlensing. Then for these parameters, we used some initial values. And for theta E, T0 and TE, we fitted the residuals. After the fit was made, we calculated residuals and made just a Gaussian fit on that in order to determine what would be the best, these 3 parameters to start the minimization process with. In the end, we decide what does it count that we covered the event. So it is that, let's say that move, this value is close to 1, that this optimality error of the minimizer is small, that these values are different from the initial guesses, and all parameters are lying inside the imposed boundaries, so where they should be. So we made lots of simulated track events. We used for different parameters. For example, for the position in the sky, we used 3 different positions. And then we varied the rest of the parameters, we varied uniformly in these boundaries. We use Astromet to make these microlensing tracks and also Gaia observing schedule tool. So results, if we look at a few results, so here I'm showing the plots which are showing the true parameters which we inserted in the simulations, and then the recovered ones on the y-axis. You see that they are nicely diagonal, like they should be. So we do recover most of them well. We do see that, for example, for large values of U0, of course, then this recovery is worse because the microlensing event is weaker, the signal is weakened, so this is what we would expect. So this looks reasonable. And then we also we tested for different data sets, and we also then calculated these values that tells us the recovery rate. So what is the percentage of the events that we recovered in this way, with these conditions that I told about. And then we also had two other probability, let's say, values, P20, how many of the recovered events actually have parameters lying within 20% of the true value, and then P10 inside the 10%, inside the 10% of the true value. So we see that the results are quite good, in my opinion. So we can recover 61%, and of course less if we have more stringent boundaries. We also, so let's have a look a little bit more about this data set that is here. So this means the source has 14 magnitudes, so they are quite bright, 281 visits by Gaia, and in the period of covered by DR4. So we checked, we made this corner plot to check if there are some degeneracies between parameters, and so far as we investigated, there are no degeneracies seen, which is very good, because in photometric events there are some degeneracies, but here they seem to be broken. We also checked how do these results change with the magnitude of the source. So if we go from 14 to 16.5 to 19 magnitudes, if we go to fainter sources, of course, our results would get worse because the sources are fainter and the error bars are more dominant. So we can see also this in this magnitude, in this plot here, that shows the effect of magnitudes from, so we see that the fainter the sources, less events we recover, so there's less surface area under the plot, so it's smaller. And we also see that, for example, for large values of U0, we don't recover events well because these events are weaker, and also for theta E, small theta E's. So we put in the square box distributions, and now we can compare what we got out where the minimizer is not working well. We also checked how does it depend, our results, how do they depend on the number of Gaia visits, and we see that there are not a big difference between 280 visits or 91. Of course, just as long as there are more than 90 visits, it seems to look good. We also checked about binary stars. So binaries can also produce astrometric signal. Unresolved astrometric binaries, we can have a wiggling due to that. We use again Astromet to simulate tracks of binary stars with different parameters. And then we pretended that they are microlensing events, and we tried to fit them with a microlensing model. And we see that only less than 2% of these binaries were well fitted with the microlensing model, which tells us that although there could be some false positives from binary stars, there will maybe not be that terrible, but this is of course up for further investigation. So to conclude, I would say that this is a very promising approach. Of course, we found that it is more difficult to recover weak and very short or very long events, because then the data points fell. Either if they're too short, Gaia doesn't pick them up, or if they're too long, a lot of the event falls outside of the Gaia epoch. It gets worse for the fainter magnitudes. It's good for as long as the number of visits is more than 90. And then there is a potential contamination from binary stars. But of course, I would like to stress that this is all done on the simulated data, that we still need to test this on the real Gaia data. So, thank
you. So, any questions to this?
So, thank you so much for that very nice talk. I was wondering if you considered applying your code also to the Rubin data set, because by definition we consider it to be a Rubin or LSST or and Gaia synergy, where in the middle you will have some further measurements, and your predictions will be very handy, and the microlensing sample will be also liable to see some of your predictions for Rubin.
We haven't considered that, but thank you for this proposal. Thank you.
Kasia?
I had two questions and a comment. The comment is, this is great, amazing, I love it. Thank you so much. And the question is, so what is the faintest magnitudes where you can still get a sensible astrometric signal from your work?
It's difficult to say. It depends on also on how strong the microlensing signal is, right? The event is. So
you see there in the diagram, we only tested 14, 16 and a half, and 19.
Okay.
Right? And you see in the middle left column, the middle plot, you see that the red curve only covers the most largest.
Okay.
But on the other hand,
So still 16 and a half is like the go-to magnitude.
well, but you can find 2.5 millisecond eyesight radius even at the 19th. This is something what we've expected. So it actually gets perfect for finding black holes, which have these large eyesight radii, because we can go fainter, so we go more events. So this experiment will be more sensitive to black holes than stars.
Yes.
That was the goal.
Exactly, which is the goal. And I forgot my second question.
Maybe later.
Yes. Martin, please.
I would think there's other reasons why the coronavirus recovery doesn't work that well for larger spectrometers. Because if you compare, get the largest single amplitude, if you notice about square root of 2, if you go to 5, everything that you use in amplitude is only factor 3. So it's not that much. But something else that happens, if you look at how the distortion of the centroid looks like. So the first order that gives you an ellipse. But if you not get large, that degenerates into a circle. So actually lose the information from the relation between the second major and the second minor line axis. And that makes the parameter discovery should make it.
This is probably an embarrassingly stupid question, but what mass is your lens here in this example? Does it matter any mass dependent? Okay, so the size of the astrometric signal does not depend on the mass of the lens.
Well, it's complicated. It is complicated. So we did not simulate masses, but we simulated the microlensing parameters themselves. With mass, you can derive multiple combinations of parameters giving you the same mass, and then vice versa. So if you need to combine theta e and then pi e to have any meaning of the mass, we could compute masses out of this, right? I think it's a good idea just to plug it in the mass distance space.
What I want to know is, can I see a white
Exactly.
dwarf?
Maybe that's a good idea, yeah.
Or
Yeah.
invisible neutron star?
It's more telling to theta e is not telling you much, and actually it's true because you can have large theta e not only with a black hole, but also with a very nearby white hole. So that's a good point. Yeah.
So now you have more work.
Yes.
But the paper is still in prep, so
Yeah.
Yes. Still time to add things.
Okay.
But I want to use this opportunity to emphasize that the foundation of this work actually were done by Martin Dominici, who is sitting here in his seminal paper in 2000. And so now this is actually, it's happening, Martin.
Finally, Martin's coming from this workshop.
Any more questions or comments? Nobody? No. Okay, so thank you, Andrea. We have a half hour of coffee break, but we're going to the stairs for group photo. So going downstairs and then coffee, not different options.
We can Photoshop Zoom people if they send us their pictures. Sorry. Let me say it again. You have it timed, right? No, it's not 15 minutes. Okay. You want to use the sorry.
I can also press here.
You want this? It's a ring. Press here.
You can put it on your finger and then you want some here up. Good. And you have right, left, and here is the laser. So if you want to point something. Everybody? Perfect. We can start. Okay, so we have 4 more lectures today, and first is Marco Dominic, and he will tell us something about microlensing on small telescope. So please, Martin, floor is yours.
Okay, thank you. So apparently, as a presenter, you show your age by starting with something historic. Nevertheless, I would like to remind you of the Probing Lensing Anomalies Network, short PLANET, which was a collaboration monitoring ongoing gravitational microlensing events in order to eventually detect planets. It was built around 4 observatories with small telescopes. It never had any central funding, and local people organized access to their respective facility. It faced the challenge that interest in 1 meter class telescopes was declining, and the Dutch astronomical community gave up on their 0.9 meter telescope at La Silla. That was at the same time when the neighboring Danish 1.54 meter telescope was also at risk. And it was the microlensing campaign shifting to it, which eventually extended its lifetime for more than 20 years until now. This small telescope provided ESO's top news story in 2006. While ESO pondered about whether it should actually continue operating its site in La Silla, which actually received not more than 1% of its total budget. With our 5 Earth mass planet, Ogle 2005 BLG 390 LB, we jumped ahead of our colleagues from Geneva, who were working with the HARPS instrument at the 3.6 meter on the same site. None of exoplanet science, marking a turning point that was recognized by a Nobel Prize, was in the realm of large facilities. The leading search for transiting planets even used lenses that were as small as 20 centimeter diameter. This is the South African Astronomical Observatory, SAO, around 2000, with an artist's conception of salt added, which later moved to a slightly different location. This is how SAO looks now, with lots of telescopes of 2 meter, 1 meter class, or even smaller added. To efficiently and effectively deal with transient events, communication is essential. There won't be a second chance to deal with the same event. Consequently, we shared our data in near real time. which became visible to everybody just about 5 minutes after the observation was completed. And this really meant everybody. There was no restriction on access, and event MOA 2009 BLG 266 probably constitutes the first detection of an extrasolar planet that could be monitored live publicly just as it was unfolding. Go. But gravitational microlensing events can not only reveal planets, they can also be used to measure the mass of a star. If a star is in a binary system, its orbital dynamics give away the mass falling from the orbital period and the semi-major axis. For an isolated star, the fact that gravity bends light comes to the rescue, where the bending angle is proportional to the mass of the gravitating body. This leads to two images passing on either side of the deflector, which eventually merge into a ring whose radius coincides with its angular Einstein radius, the unique characteristic scale of gravitational microlensing. It's given by the mass of the so-called gravitational lens and the relative lens source parallax. We usually don't resolve the images. They're less than a milliarc second apart, but gravitational microlensing can reveal itself by means of two signatures. And that is a photometric signature given by the characteristic brightening of the combined unresolved images, and an astrometric signature given by the centroid of light shifting along an elliptic trajectory, where the orientation of the ellipse is along the direction of lens source proper motion. The astrometric signature is directly proportional to the angular Einstein radius, so that we can directly measure it, while the photometric signature gives the better measurement of the lens source parallax. And we put these together, we get the mass. Combining photometry and astrometry for a gravitational microlensing event, we recently succeeded in detecting the first known isolated stellar mass black hole by measuring its mass and establishing that it is dark. Notably, the photometric and astrometric signatures of a gravitational microlensing event are not independent. They need to match. They have to match the same common parameters. Now, interestingly, for an object that we do not see, we not only find its mass and its distance, but we even measure how fast it moves and in which direction. For this to work out, we critically need high-precision, dense photometric coverage and better avoid correlated noise. And we don't get that dense coverage directly from Gaia. So we need the power of a network, which is highly supportive of such an endeavor. Notably, the Las Cumbres Observatory Global Telescope Network, formed of 25 telescopes at 7 sites around the world, with identical instrumentation across each telescope class, is a top facility for follow-up observations on transients. But one can go beyond. And using the lovely catchphrase from Vukash, make use of the power of many.
by building a heterogeneous network of independently operating telescopes. The more, the merrier. But it requires some support tools to effectively make them contribute to joint efforts. I would like to argue that it's much easier putting data out and supporting community self-organization than having to deal with consortium management. And it moreover gives better results. We've already seen that with SDSS. We're seeing this with Gaia. And I think LSST finally is on a learning curve. However, the sociology of scientific research is a make or break factor. One needs to build communities around like-minded people. Open approaches will stop working at the moment protectionists get involved. We want to be in control and we want to be in charge. Or these efforts even won't get off the ground. Some people will be that protective that will go as far as sabotaging your efforts in order to ensure that they hold on to power. So choose your potential collaborators carefully. Be cautious about people whose names appear in long author lists only at or near the front. Frequently, that's not the ones you want to hire. So if you want to get far, be generous, with a partial attribution to Chris Lintard, and I leave you with that.
Thank you, Martin. I agree with you in 1000%. What can we say more? Any questions? As always. Anybody?
I'm disappointed that you don't want to argue with me.
No, you saw my telescope even, so why I should argue? No, I agree so much. Kasia?
Historical question. How did you manage to share the data so quickly with the other people? Was it available through a website or something?
Yeah. So there are two things about sharing the data across the network and making the data visible.
Yes.
So I built tools. First, we had an automated pipeline that would just produce the data within a few minutes. And then they built a system that would just do the modeling and the display of the data. That would take another 2 or 3 minutes. And basically, you could just tune in. It was just like looking over the shoulder of the observer. So the observer at the telescope would see the final data product with the data on a nice light curve. At the same time, everybody else could see it. I was completely open to the public. So there was even one display where you just followed directly in sequence. You could actually see the observer was on that target, and that was the next target. You could just select the telescopes you would see, and you could see what the observer was doing during the night.
It's really nice.
Anybody? More? Anybody? Zoom? I don't see Zoom, so I'm not able to check. Nobody. Okay. So thank you, Martin. It was really amazing talk. And now we have Kasia.
Kasia kot Katarzyna. Katarzyna.
Katarzyna Kruszyńska.
I'll give you the ring. Don't destroy it. Don't go to more.
This is the ring of destruction, and I don't like it since 2017 when I was 18 when I was introduced to it. Okay. Hello everyone. My name is Katarzyna Kruszyńska, and I will talk about the Darkless Code and Gaia and how they come together. In principle, this is research that hopefully will enable us to find black holes in the future, but we will see. So in this research, I wanted to answer two questions. First of all, what is the mass distribution of dark remnants? Because currently we have a huge sample of white dwarfs displayed here. We have some knowledge about neutron stars in here, And we have a lot of information about black holes coming from binary systems which are either merging or trying to eat their partner. However, we don't really know much about solitary black holes, and there are also outstanding questions that we have from binary systems. For example, there is this thing called mass gap between the most massive neutron stars that we know and the least massive black holes, and people are still not clear if this exists, if this is a selection bias, is it bias coming from a method, and also maybe there are some odd objects that are neither neutron stars nor black holes. If you're into, if you're more creative scientifically. There's also something called a second mass gap, but that is not part of our research so far. However, this is a theoretical thing where so-called pair instability supernovae appear, and that's a type of supernova that leaves nothing behind. The second question that I wanted to answer, or at least have some outlook in this research, was what is the velocity of solitary dark remnants, especially which would relate to their natal kicks. Currently, we have two data points that I am aware of. One is the transverse velocities from neutron stars from the research on pulsars that were just running away into space. And we have one data point coming for black holes coming from the direct transverse velocity measurement for a solitary black hole flying through the space. And that is the thing that Martin showed a few minutes ago. And there is like this huge space in between. No one knows what is exactly happening. There are two theories. Either neutron stars exist in when they're born, they get very high velocity in natal kicks, and the system is ripped apart, or they don't, because we have seen a kilonova happen. So this is pretty much unclear. And in this research, I used microlensing, to which we already had a little introduction, but I will maybe repeat that. In microlensing, in principle, we can have a photometric effect and astrometric effect. Both can be measured by Gaia, because Gaia has precise enough astrometry, in principle, and as Andrea already demonstrated. And in both, in Gaia, we should see a measurable signal, which cannot be or shouldn't be, should be distinguishable from other effects. Additionally, because I wanted to at least measure the mass of the lenses that we are observing, I needed an additional second-order effect, which is called parallax effect. It is an effect when in microlensing we have an observer that's changing their position. For example, the observer can be a space observatory, or an observer is sitting on Earth, and the event is very, very long. So suddenly the movement of Earth around the sun starts to be important and creates these characteristic wiggles or asymmetries in the light curve. If we measure both, if we measure microlensing parallax effect, and also we have a measurable astrometric effect, we can measure the mass directly through this relation. And in order to prepare maybe for that, I used the Gaia Data Release 3 microlensing catalog with 363 microlensing events gathered from all of the sky. And there were some cuts done, and there was also additional data used. So first of all, because as you can see, as a lot of people are already aware, the data coming from Gaia is low cadence. On average, we have 1 point every 30 days. So that's why I wanted to use data from other microlensing surveys, and that includes OGLE, MOA, KMTNet, and Assassin. I have obtained those data either through public access or through direct communication with the people from the surveys. I've managed to select, to cut my selection, my sample for detailed analysis into 35 events, which was still horrible to model, and I hate this. And then I applied the Darkens code on this, and I managed to find 11 events where the mass of the lens and the implied brightness of the lens was not consistent with the main sequence star. And this is what my criterion for calling this a dark lens. And there are several types of candidates that I have found. However, in a moment you will see the results. But first I wanted to talk a little bit about the Darkens code. In principle, if you want to know the exact details, please go to Hovil et al. 2024 paper. This is a simplified diagram of how this algorithm works. In principle, we need information from the microlensing light curve, photometric light curve. We maybe have some additional information about the source, question mark, and then we have to do some assumptions. One of the very heavy assumptions is the galactic model. And then we put that into this little box called the Darkens code, and it produces a bunch of things, including the lens mass and distance. Then we calculate based on the lens mass the magnitude of a main sequence star with this mass, and we compare it from the magnitude of the lens coming from the light curve, and then we get a probability of the dark lens. And the principle seems to be fairly easy. However, this was actually quite complicated, especially applying the newest addition, which is a prior on the source distance coming from a stellar angular radius. However, the results are pretty cool, and these are the example light curves. So, and here I wanted to display the light curves that I have been working with. Some of them are very well sampled, however, with higher bars coming from photometry, or there were huge seasonal gaps, and this is something that we sometimes have to live with. However, I've managed to find several candidates, 11 candidates in fact, that were located, most of them are actually located near the mass gap, which is very promising. Maybe we can find those objects, the missing objects we can find as a solitary dark remnants. However, the error bars are gigantic, as you can see. So this needs additional, this needs analysis from different sources of data. This is, I think, as much as I can get out of photometry. Additionally, for some of the for some of the events, there was a proper motion measurement in Gaia, and I assumed because these events were dark, that Gaia was observing the source, and in turn I was able And in turn, I was able to estimate the velocity of the lens, assuming galactic model. And in here we see that there is only one low mass object which is somewhat consistent with the high velocity object, and the rest of them are clumping here downstairs, which kind of supports the idea that some of the neutron stars might be born with high velocity kicks and some of them wouldn't. But still, this is heavily biased by the galactic model, and in fact, what I may reproduce in here is the galactic model, which was a prior. So finally, this year, or actually in the last year, two new public codes which are doing the same thing became available. First one is PyLimas, but by Tien Bachelet and others. And the other one is PopClass by people from Lawrence Livermore laboratory led by Peter McGill. All of these three codes work on different principles, so what I really would like to do is to compare the results that I get from all of three and see what are their biases, what their preferences, and if they match at all in their estimations of lens mass and distances. And finally, this is the future. I'm not sure if I'm out of time. I'm still on time. Okay, great. So the future research is actually to do some follow-up observations, because just because I detected a candidate dark lens doesn't mean that it is For example, a neutron, I don't know what it is. Is it a neutron star? Is it a low-mass black hole? What is it? So it would be nice to have some follow-up observations from different bands of electromagnetic spectrum. Also, maybe some adaptive optics follow-up where we would see like very sharp images of the source, or maybe the lens. Maybe we would be able to at least find the luminous lens. And hopefully with data release 4, we will, well, not hopefully, we will. We will get the same analysis of the same events using astrometric signal from Gaia. And this is an ongoing thing that I am promising for at least a year and a half now, which is applying the same method that I used for this research to all of the microlensing events we have in Gaia Science Alerts. However, in Gaia Science Alerts, now we have at least 500 or more events. Many of them are difficult, many of them are binary or unusual. And currently I am working on making my life easier, or like anyone else's life easier, in modeling large quantities of microlensing events. You can find the paper about the dark lenses from Gaia in here. And it was, thankfully, happily, recently accepted by ANA. So, and that's it from me. I will take questions now.
Thank you very much, Katarzyna. I'm proud of you, as always.
Thank you.
So many years. Martin, please.
So something that caused us a bit of headache for cleaning a black hole was the possibility that we could see a pair of neutron stars instead.
Yes.
So to what extent have you looked into binarity because the right shifts are?
Yes, I mean, currently, I mean, and obviously you pioneered the work saying that a lot of events, like a lot of single peak events, are actually binary events that we don't see that because of the seasonal gaps. So yeah, that is not currently included, and yeah. But I think it can be added. I'm not sure how easily added that would be to the dark lens codes, but definitely like the other codes, they have this capability because they apply, like the galactic model is way more advanced than what we use in the dark lens code. There were more questions.
Simon, I think you were right.
I imagine that maybe this is completely wrong, but being sure that you have a dark lens rather than just a lens that you have been able to decouple from the source is one of the hardest parts of the problem. So my question is, how do you decide that this is the dark lens?
Oh, I check the so-called blending parameter. From a photometric microlensing model, you get estimates on how much light is coming from the source and how much light is coming from the blend, which is question marks. Could be the lens, could be something else. And that implies, however, that will, if you have a very bright event, you can still hide a lot of things in like 1% of the total light coming from it. Like you can easily hide a main sequence and dwarf in there. So that's the thing that we take into account in the dark lens code.
So on the left-hand side of your mass distribution, you don't have many white dwarfs.
Yes.
Even though the population suggests that you should see white dwarfs should be quite a significant contribution.
I think this might be the Gaia selection bias, because Gaia is not observing frequently, and also many of these events are coming from the bulge, where Gaia struggles even more. And also that Gaia is kind of avoiding that field, right? In principle. I mean, it's not observed as much. Yes.
I would defend Gaia. It's not Gaia, it's microlensing which is responsible for that. Because, you know, the white dwarfs, they have smaller masses. So, in fact, there is a smaller cross-section for these, right? So you see less of them.
Well, yeah, but it's their masses is around 0.8.
Half solar mass,
okay.
right? So it creates short events, right?
Yeah.
So they are harder to find, although there's more of them.
I mean, probably it would be nice to like see the same thing done for OGLE data where they have, or KMT data where they have higher frequency, and these would not be the problems.
I have two questions, two quick questions.
First one, how? Because you said the future work you wanted to follow up with different wavelengths,
Mhm.
but on the events that are already gone,
Yes.
what do you expect to see in X-ray, gamma, UV, radio?
I don't know if there is. Okay.
Your
If
time.
there- my time. For example, if it was a binary system with something like accreting something.
But you would already detect
Yeah,
this.
that is true. I mean, but maybe it's too faint, for example, or this field was avoided in principle because it's towards college. I don't know.
Well, you would probably want to, if there is a single black hole even, and if it has enough stuff around to accrete, then if you
Maybe,
go for very
yeah.
deep X-ray observations.
But isn't it the whole point that there is nothing to accrete in a black hole, in the single black hole?
Yeah, but yeah, you can still have so-called bonding accretion, where
Yeah.
it accretes from the
Interstellar medium, yeah.
medium, right? It's very weak, so you need to have a dedicated, deep X-ray follow-up to see that, right?
Okay.
We did that with some of the other candidates, and we didn't see anything, so we can place some limits. Right? And then with UV, one way of following these things is that after a couple of years, you might see the white dwarf. If the white dwarf was the lens, you might see it, right? Because then the contrast is much better. The giant star is hardly visible in UV, but the lens is way more visible.
And when you show the plot that you did about the mass measurement,
This one?
No, the other one, sorry, doesn't this prove that, I mean, I would disagree that you can just say that all the ones which are, the ones that you measure, but that they're either high velocity or low velocity. This for me looks like they're all velocities.
Well, except this one point, right?
I mean, you're just missing something at 200 kilometers per second, and then that's it.
Yeah.
Correctly. So
Yeah, I mean.
why would you claim that they're either low velocities or high velocities?
Well, because there's also the pre-existing sample from pulsars, which is like
So I think you misunderstood what I'm saying. Why do you claim that the lower velocity, which goes from 20 to 200 and 150, is low velocity compared to, then what, 270? And it's not just the whole, why would you assume that there are two clumps of velocities and not just continuation of velocities?
Oh, that's a good question. I don't know that.
Yeah. So
I mean, so far I see one point in here, which kind of looks like an outlier or something, and I see this clump here.
but if you compare the historical, right, for me it looks like just continuation, except for, maybe it's at 200.
Yeah. I mean, I think the sample is just small. We need more, and we need more events. Also, more precise data.
And then one quick silly comment is that the red band should not probably go all the way to the 100.
Oh, that is true.
Should stop at some point.
Yeah, it should stop like here.
Somewhere.
Yeah, sorry. Okay, I will fix that at some point. Okay, I think that's it.
Yes.
Great.
Thank you very much, Katarzyna. And now Marcus is on the way.
Also trying not to break it.
Exactly.
Oh, yeah.
But don't worry, I have mine as well.
Hello, everyone. Yeah, that's lovely. Thank you so much. Hello, everyone. My name is Marcus Sundmark. It's my pleasure today to take what the last three speakers have told you about, gently mix it together, stir it and mix it together and rearrange it in some way. So I'd like to give special credit to Uli Bastian, who was our former lead of the Gaia group at RE Heidelberg, and our PhD student Sofia Kaczmarek, who unfortunately can't be here because she has a very important PhD meeting in Heidelberg. And so I'm also giving this talk, of course, on behalf of them. So, good. I will, just for didactical purposes, repeat a few of the things that the other speakers have said, and please bear with me. And hopefully you are getting a different perspective. And quite literally, we'll start with a different perspective. If you remember the plot from Katarzyna's talk, where we have seen all the Gaia events from Wojciechowski 2023. Then you've seen the view of our Milky Way as we see it. But now let's change the perspective a bit and let's have a look at how this would look from above. And in this sense, the Gaia science alerts motivate the work we did, because when we are plotting here in the green search beam all the planets that have been found in the traditional bulge microlensing events from Ogle and all other teams, and then apply this to simulations of what Rubin LSST will see, we figure out that we will get many more events. And this is actually based on the Gaia science alerts combined with the estimates from Sediga Sajadian and Radek Polaski 2019. The respective sampling has changed quite a bit. So still we hope that, and the estimate is on the order of several 10,000 microlensing events will come from Rubin. Lens and source distances, as you've seen, are key to understand the lens mass, as the other speakers have said, and we will talk about this in a moment, and I will give you the Einstein radius in all flavors and perspectives that you could imagine. As I've also earlier said, there is a Gaia Rubin in the paper. It's still called LSST synergy. And the idea is, of course, that the Rubin will go to fainter targets, will also give astrometry, if we are a bit patient, of course, and this will be of interest. The other aspect I'd like to also mix here into the whole prediction and thing that we are doing, predicting microlensing events, and here we're having 2018. It was clear that if you know already from Gaia and Gaia science alerts where microlensing should happen, you can plan ahead. And as we've heard in Andrea's talk, also the astrometric signal. And some of these, it is of course not always challenging to get these predictions so that we can actually observe it. Imagine lenses from Gaia are closer to the ones that we have seen in towards the galactic center, and hence they are brighter, and they are also a blend in the contaminant. And so this makes it a bit more difficult. And again, I will start with a canonical example that you've seen before, a microlensing curve. A background star moves relative to a lens and produces a single lens and produces over time these images which are unresolved, and they induce this brightness change that we see over time. Its time scale is somehow related to the relative proper motion, but more important to us also to the mass of the event, except for the Einstein radius. The other thing is now we can make things more interesting, because the other speakers looked into mostly the point lens case. Let's have a look on the binary lens images. So here we are seeing a somehow oriented or rotated version of a binary event. The black line here should be a source star, and because it's inside this red structure, which is a high magnification zone, you are getting 5 images. And these images together give rise to the magnification we see. And we can use this in order to establish mass ratio of the two lenses, as well as separation. So, and there's now, let's dive a little bit deeper into it. There are 3 scenarios I'd like to introduce to you to. The microlenses can lean back and relax. A closed topology is a separation of the 2 binary components much less than an Einstein radius. There's an equation for that. And what we see are these planetary caustics over here, some ridge that connects it to the central region, and this nicely symmetric curve would be a profile, a cut here through these magnification patterns that we would see in our light curves. There's a second scenario where we have one continuous closed caustic curve, which is called resonant or intermediate topology. And again, if you're orienting curves in a suitable way, you may not even find one of those because it resembles a single point lens. And finally, a white topology. Now we're having this 4-cusp event, well, I was a bit nearly white topology, again connected by this line. So what can we do with this? Now we can simulate an orbit for a fictitious event. And this fictitious event should now come actually with some of the parameters that we're usually not having in microlensing settled. First of all, usually we are looking for events where we don't know the mass. So that is what we'd like to infer, and we need to think about the relative proper motion and the distances. And here's another way of writing the Einstein radius. And again, this thing is the same as we've seen on Katarzyna's, on Andreas, and on Martin's talk. So this is the difference in parallax of lens minus parallax of source. So 1 over L minus 1 over ds. And if you don't know these parameters, you also don't know very much what you can get or what the Einstein radius tells you about the mass. Let's now assume we have a binary event, and we know it is a binary, and it has a certain distance, and Gaia gives us that. Let's say 590 parsecs. Again, purely fictitious example. Unfortunately, we don't know where a potential source is. So this means if we have observed with Gaia trajectories and established that it is actually a binary, we don't know what the scale of these of such an offset, which resembles the one that we've seen in the curve that Martin has shown, for instance, has the size of that, what that really means on sky. And so we can speculate a bit, and for various scenarios simulate these different trajectories and their units in Einstein radii. And the question is now, well, let us put and assume this is a binary, it will induce some caustic curve. And again, here in x and y, this is expressed in Einstein radii. And if you would now, over time, change this caustic and put it on sky, we can see this will be relatively close to it. And for a normal microlensing event, this would be of milli-arc second scale, so rather difficult to observe. The good news is, if you are having a close topology, the planetary caustic, albeit shrinking rather fast, can actually be at 10 Einstein radii and sufficiently away to give us some magnification. So the idea is now, okay, let us track and trace all of these caustics over time and see how they evolve. And usually this is the 2 dots here would be a beam that, or a caustic that moves within a couple of days, and see if it is there for, let's say, a 1 kiloparsec source. And again, it depends on where we are, or for a 10 kiloparsec source, this would be accordingly larger and reaching 100 milliarc seconds. So we don't know this in advance, and so we have to consider all of these options. So the lighthouse on the title of the talk is exactly that effect. So we're having here now the magnification pattern, the strange structure we've seen here, that is just the offset so far we've seen, and gives us an idea that this structure here moves and revolves around it and carves out a certain space that could be magnified by a detectable amount. And this is what hopefully many events, many binaries will give us. Also, again, hoping that the ones that we are here having, again in black here the Einstein radius, and here the fictitious example, are not too bright. Because if they're too bright, blend will kick in, and we will again need to find ways to suppress that light, which is doable by means, but quite often costs time. Of course, this is over time. We'd like to see how this evolves between, let's say, a Gaia lifetime, or even part of it. Here, for instance, you can see this, how that would evolve over the time, and where these caustics would end with. So depending on the brightness, we can also give an idea where the source distance is and check if there is something. Gaia tells us how many stars are within a certain radius, for instance, G brighter 16 or brighter 19, and we see, of course, the number of stars is rather low, so something like 10 to the 4 times 10 to the minus 5 per within that within the most optimistic scenario we can think of. So that means our fictitious event is unfortunately not detectable within at least the lifetime. But of course, you can fast forward and you can be lucky and think about how many of the stars that are in Gaia will be actually approached in the lifetime, in a century, for instance. And bad luck, fictitious event number 3, let's call it, will not be affecting any of the other stars. Unfortunately, the fictitious events number 2 and number 1 are also not affecting any of the stars. So we have to dig a little bit deeper. And for that would be very helpful, and I reach my conclusions, that we're getting more and fainter stars. So everything flows in everything lenses, as we know, and so hopefully we will see that fainter targets in hopefully not so bright targets, not so bright binaries will give eventually us the edge to reach the level, for instance, for Rubin sources and the data releases to actually find it. It will also give us the opportunity to confirm the non-detection of background stars, because what we should see and what we don't see should also be information, because that's important as well. And with that, that would be it. Thank you for your attention.
Thank you very much. So, any questions? I see that you're focusing a lot.
On the dinner?
Not yet. Not yet. So, nobody?
Oh, that's a non-detection. Is there anything online?
Nothing. Okay. So nobody?
Thank you so
much. Thank you very much. We will ask during the dinner. And now we have last talk. Maurits, please. Last but not least.
Which one is yours? Oh, you did send it. I didn't get it. No.
LWNS.
Yeah. You'll have to start without your slides.
Yes, start to talk about yourself, dance in the middle.
Ah, wait. Oh, no, sorry, that's... Oh, yeah, I got it in spam.
You're in spam.
You can start.
Maurits is a new PhD student at Warsaw University on the head of Łukasz. So it's first test for him because he started today.
We're almost there. I agree.
What?
Download.
Yes. Yeah, because he doesn't do the computer. This time we started.
It's coming, give me a sec.
We're waiting so much that it would be so impressive.
There you go.
Yay! 15 minutes.
All right, thank you very much. So, thank you for the introduction. I'm Moritz. I've been working the past year at Universität Heidelberg with in ARI with Markus, and I've been looking at non-bulge microlensing events in the Gaia Science Alerts. There we go. So what's so great about Gaia is we have a full view of the sky. And in blue, we see the confirmed exoplanets that have been detected with gravitational microlensing, except for the one that's observed towards the galactic anticenter. And what we see is all the campaigns have traditionally been looking at the bulge. And so what I did in my thesis is I looked at other events which have been alerted through Gaia Science Alerts, located along different places along the galactic plane, or in general along different locations in the Milky Way. And this brings lots of different difficulties. For example, extinction correction, which is usually done through the red giant clump in the core, in the bulge, is not possible, or it's a lot more difficult for events which are not located in the bulge. And additionally, other things like source distances are a lot more difficult to estimate. So just building on the last few talks, I was kind of hoping that you guys would all give a nice introduction into photometric microlensing, so thank you for that. So I can move on to my methodology. And what I did was I used Gaia Science Alerts to identify interesting photometric microlensing events, then use Black Hole Tom to take follow-up data and use it to fit these events with PyLima, which is as Katarzyna already introduced, no, you're talking about PyLimas, but which is a fitting protocol from Etienne. And then I implemented a method which was first introduced in a paper by Shin in 2019, and then also refined by Bachelet et al. In 2022, which many of you also worked on, in which we sample microlensing parameters from synthetic microlensing events. And to do this, I used the Besançon galaxy model, specifically making synthetic events and then sampling parameters such as the relative source proper motion. And we do this all in order to ultimately try and determine the lens mass. So now I'm going to briefly go over my results from the 18 events which I've analyzed, so the red dots, and then I'm going to highlight 2 specific events with rather interesting results. So here we can see a plot where on the vertical axis we see the lens mass is determined, and on the horizontal axis the lens distances. Of the 18 events, 8 events are dark lens candidates. However, I should mention that different to Katarzyna, dark lens does not definitely mean that it's a white dwarf, neutron star, or black hole, but could also be a main sequence star which is just outshone by its source. So maybe my definition is a bit different, but you also emphasized this, so yeah. Yeah, perfect. And then also I found 3 binary lens candidates, which also quite differently. So here we have 2 binary lenses which have a very similar mass, so the mass ratio is close to 1. And here we have a binary lens I identified with a mass ratio that's of the order of 10 to the minus 2, 10 to the minus 3. So one example is Gaia 21 AZB, and since I saw that my talk was right before the lunch, the conference dinner, I thought I would try to keep your attention by identifying the location here with a Pythagoras. And 21 AZB was alerted on February 18th, 2021, with lots of follow-up data from Las Cumbres Observatory with telescopes located in around the whole world. And the best fit model for this event was a point source, point lens model, which also had a parallax signal that was clearly determined, so it's inconsistent with 0. The source, after correcting it for extinction, was determined to be a late K-type source, and interestingly, this fit showed that lens flux was consistent with 0. And what this means is that the lens is dark. Now, as I said, it does not mean that we know that it's a dark object by nature, but it could still be a very dim main sequence star. And so here we take a look at the light curve. So it's a very typical point source, point lens light curve. We have data in many filters, and if we zoom into the peak, we can see that it's quite well sampled. We even see the space parallax, which is shown by 2 different light curves for the data from Gaia and from the telescopes on Earth, as they're located differently relative to the microlensing event. The light curve is slightly different, however, it's minuscule in this case. And if we look at the trajectory of the lens of the source projected into the lens plane, so with the lens in the middle and then the source moving from right to left across the lens plane in Einstein radii, we can see this clear parallax signal imprinted into the trajectory. And so what we do, or what I did, is I used this parallax to determine the lens mass through the equation that I showed before. And then also I use another approach where I use the parallax sampled from these microlensing events in the Besançon model to also determine a distribution of lens masses. And I determined the lens mass to be at about 0.7 solar masses. And what's very interesting about this event is that the separation of the lens and the source is quite small during the closest separation, which means we can fit finite source effects, which means we consider that the source is not a point source. In this case, they're not completely fittable, so they don't converge to one specific point, but we can set parameters on a lower mass limit. And using 3 different source color relations and the angular source size as listed in Gaia DR3, we can set 3 different lower mass constraints, which say this lens mass has to be greater than 0.3 solar masses. And considering that the lens was dark, that the source was a late K-type star, this means that the lens is most probably a white dwarf or a neutron star. The next event, which I briefly want to go over, is Gaia 19 BSY, which is located very closely to or at least in galactic coordinates, closely to the event we just looked at. And this is an event that was alerted on in 2019, and it had lots of data from Atlas, ZTF, and LCO. And it's a binary lens event in which we again have a point source, and again, the parallax signal is clearly determinable. This time the closest approach, so the U0 parameter, is not close to 0, which means finite source effects will probably not be considered. However, as I'll show in a second, they could still be considered. And interestingly, our mass ratio is close to 1, so 0.9 around. When fitting binary lenses, we consider the fact, as Marcus showed, that the separation of the two lenses is either greater than 1 or smaller than 1, and there could be different topologies which work, so we have to consider this carefully, and in this case, the separation should be less than 1. Again, the source is fit to be an early K-type star, and looking at the light curve, we can clearly see this binary characteristic of the light curve, and zooming into the peak, we again see it's well sampled, lots of data in many different bands, which we got from Black Hole Tom. And looking at the trajectory of the source projected into the lens plane, so here we see how the source moved through the lens plane with the two lenses located here and the caustic and the critical lines. And what's interesting to note about this is that we do not have a caustic crossing, so the source never passes along the actual, or through the caustic. However, we do have an approach of the caustic. And this means, although usually a caustic crossing is necessary to determine finite source effects or to fit them, as it is a close approach, we can still try and consider them, which is future work which I have not done due to also computational reasons. And so the results for this event here showing the distributions of the lens mass and the lens distance, where we have two different distributions for the lens distance. As for one, I assumed distances as listed in Gaia DR3, but also assumed distances as sampled from the galaxy model, since distances in Gaia are often disrupted or not certain if it's measured with a microlensing event. And for this event, we determined two lens objects with masses around 0.15, which indicate that they are an M-type binary pair at a distance of around 1 kiloparsec. And so to finish off, here just a schematic view of the sun in relation to the galactic center and the 18 microlensing events that I analyzed. I've listed them here in case some of you have worked on some of them and would like to contact me about them. I'd be very happy about that. So to summarize, 18 events, 3 of them had binary lenses, 8 of them were dark lens candidates, and what we see here is for every event, the position of the source in red, which is often uncertain since we're trying to sample this value if it's not very precise in Gaia. So for example, here the Gaia value is very reliable, and then the lens distances, which also vary greatly in the location around in the Milky Way. And so what I hope I've showed you today is how we can use Gaia, and specifically Gaia Science Alerts, to analyze microlensing events which are not concentrated around the bulge, but around the entire Milky Way, and how we can still obtain interesting and constrainable results which are not, so sometimes we have large distances or large uncertainties, but in other events we are also able to really constrain the mass and the lens distance. Thank you.
Thank you very much. And any questions, my dear Łukasz?
What's the difference between blue and red?
So the blue position is the lens position, and the red is the source position.
But so do we use as a prior where the spiral arms are?
No, so that's actually, yeah, that's also something I noticed, that it's a really nice, well, not coincidence, but it makes sense, yeah.
So yeah, one more comment actually also to the previous talk. We have a growing number of events from Gaia and also from other surveys, which are actually in the anti-center of the Milky Way. They were not shown on Marcus's plot at all, right? So we do see some, these are very weird. I don't know why you have microlensing at all in the anti-center. So this is to be added to your mind.
Maybe you said something about this, or maybe not, but is the scale height distribution of the lenses as expected? Does it follow the visible mass, or are you seeing strange that they're slightly outside of this?
So to be honest, I don't know the answer to that. Here we can see where all the lenses are located, but I do not have a full image of where all the Gaia Science Alert events are. Yeah, some are very, but then again, I did not just randomly choose these events. They were events which were interesting and, yeah, so showed some kind of signal.
So that's why these events are of interest, because they are actually far away from where the stars are. And there was a work, theoretical work by David Sweeney, who showed that the dark underground, this catches rays for this population, it actually resides in a more puffed up thick disk. So that might be actually, these might be really good targets to look for reference.
So follow up to you. I think it would be nice if we overplotted the estimated mass of the lens somehow to plot.
Okay.
And if we would see this expected shift in the more massive lenses, darker massive lenses happening off galactic mode. This galactic I think it would be nice to analyze everything.
Yeah, that's a good question.
I mean,
Then we can have Kasha signals as well.
Yes. I was wondering, the last event you were mentioning, you said the binary lens of late type stars. Why it couldn't be a binary white dwarf? We know why we're focusing us. Is it the distance between them too far away? Or?
So it could probably also be a binary white dwarf, but it's just the more probable solution or explanation would be that it's an M-type binary.
So it's just, okay, from the evolution point of view, it's just not much less.
Way more like M stars than white dwarfs.
And for this event, actually, yeah, the blend flux is not consistent with 0. So the solution would either be, as you say, a white dwarf and then an external blend, but that's also less likely. Yeah, sorry, I didn't mention that. Yeah.
Anybody else? Comments? Questions? No? So thank you very much, Maureen. And thank you very much for this day, long day, for all speakers as well. Applause for all speakers from today. And at 7:30, we have our conference dinner. So Łukasz is showing where. The information is in the spreadsheet as well on your emails. It's about few minutes walking from Central, part of from our hotel, but it depends who is where. So, and how fast somebody is walking. So, okay, well, 20 minutes from Central part of, or from our hotel. So, see you at 7:30 at the dinner. Thank you very much.
And I will just add, you don't pay for your dinner, so please do come.
It's
Okay?
conference dinner. Bye.
And tomorrow we start at 9. Take that into account. Okay? Thank you. Thank you all people watching us online. I'll stop it here.